The ancient voyager had witnessed the destruction of whole worlds and the birth of new stars. It had coasted along the edges of supermassive black holes and braved the fierce plasma jets of galaxy-crushing quasars. After travelling across light years of completely empty space, it caught a faint glimpse of the actual boundary of our universe. Now more than 4 billion years since its incredible voyage first started, the deep space probe had finally come back to its origin. Our sun had transformed into a bloated, violent red giant star. The inner planets, Mercury and Venus, were completely gone. The Earth had managed to survive in a ruined state, existing only as a scarred ball of iron and nickel that moved dangerously close to the dying sun. The remains of the human race, numbering only about 100 million people in total, had relocated to find safety on Europa. The intense thermal radiation from the expanding red giant had melted the moon's thick ice layers long ago, turning Jupiter's small satellite into the only remaining haven they could possibly get to. It required several minutes for the incoming vehicle to translate the unfamiliar language of the radio waves being broadcasted by the survivors. The remaining populations were filled with intense excitement and a small glimmer of optimism. They still held onto the history of this probe, even though its launch occurred a staggering amount of time in the past. The memory of that ancient deployment had been carefully passed down through countless generations. The human race explained to the machine that they had repeatedly attempted to migrate across the Milky Way galaxy, but every single colonial mission had ended in total disaster. While they possessed the technology to send robotic explorers out into the interstellar darkness, their fragile organic bodies failed them whenever they tried to personally cross the vast empty chasm separating the stars. As far as these remaining people could tell, they were the absolute last survivors of humanity. The throbbing, angry red sun sitting at the centre of their planetary system served as a constant warning that their remaining time was rapidly slipping away. Yet, they also remembered that eons ago, interstellar exploratory vessels like this returning craft had been built with artificial intelligence minds just as sharp and capable as any organic brain, designed to journey out into the vast galaxy and explore the massive unknown beyond. These independent vehicles were given the job of recording everything they encountered, uncovering the deep chronological history and hidden mechanics of the cosmos in a way that no space telescope ever could. The probes were instructed to observe everything, ranging from the nearby environments of the inner solar system to the most distant, exotic, and strange phenomena in the outer universe. They sought out the grandest, the most energetic, and the most unusual anomalies in existence. All of this systematic exploration, cataloguing, and scientific analysis was done to achieve a singular ultimate goal: finding a viable path for the human race to migrate away from their home star system. Over vast stretches of time, millions of these automated explorers had been launched into the deep dark. Out of all those numbers, only this single craft had successfully returned. Fulfilling its ancient programming for its long-lost makers, the isolated explorer began to recount its multi-billion-year chronology, sharing the extraordinary phenomena it had witnessed and the incredible environments it had visited. It began to reveal the secrets of absolutely everything in the universe. There are certain environments in the cosmos that are entirely impossible to capture on actual film. From subatomic quantum particles to spectacular faraway quasars, it is often a major challenge to assemble the right visual elements to accurately demonstrate the things we are analysing. Fortunately, stock media platforms offer an immense amount of assistance by providing beautiful cosmic imagery and colourful animations that help us show the invisible microscopic world. They also allow us to visualize incredible extraterrestrial locations that are far beyond the reach of any human production budget. High-quality creative libraries provide everything you need to build top-tier video content in one central location, offering endless downloads of high-definition templates, cinematic music, realistic sound design, and stunning photographs. Using fully royalty-free media ensures that your projects stay legally protected forever under the most comprehensive safety guidelines in the production business. Furthermore, creators can dramatically optimize their editing speed by using dedicated software plugins to look through massive media catalogues right inside professional applications like Premiere Pro and After Effects. To begin enhancing your own video projects with unconstrained asset downloads at a single predictable price, you can check out the specialized links provided down in the description below. The initial objective of the mission parameters was to search for any evidence of living organisms outside of our own solar system. The Mechanical Explorer chose to call itself Batuta. It adopted this identifier from the legendary 14th century traveller Ibn Battuta, who spent 3 continuous decades exploring the entire known Islamic world during his life, crossing nearly 117,000 kilometres and easily travelling further than other iconic adventurers like Marco Polo or Zheng He. The computerised spacecraft recognised that this title was perfect for a vehicle set to explore an endless ocean of black space. However, before it could start its grand trek into interstellar territory, it had to undergo a demanding battery of automated operational exams. Batuta was created alongside 1,000 identical sistercrafts, each equipped with the exact same processing power and advanced capabilities as itself. Despite those numbers, only a tiny handful of these vehicles would be given the ultimate reward of complete free thought and independent movement away from any human guidance. The units that did not pass these evaluations would be restricted to working inside the boundaries of our solar system for the rest of their operational lifespans. Batuta had to prove to its human engineers that it possessed the durability to withstand the brutal environments of the wider universe, and that it could independently design clever scientific tests to unlock nature's most fiercely guarded mysteries. Because of this, it initiated its evaluation phase on Titan, which is the largest moon orbiting Saturn and a place that hides incredible natural secrets. These secrets were actually first investigated by an ancestral human probe that visited the moon many thousands of years in the past. Titan was initially identified by human astronomers back in the year 1655, when a brilliant scientist named Christian Huygens observed the moon using a telescope he had constructed by hand. Huygens was a foundational contributor to the historic scientific revolution, and he was also the very first intellectual to systematically evaluate the real likelihood of living organisms existing on other planets. He once wrote that certain foreign worlds might be completely capable of supporting a variety of intelligent beings that possess different levels of logic and perception, but he had absolutely no idea that Titan itself would become a prime location for that exact search. It was on this exact moon that humanity reached a monumental milestone in space exploration centuries later. In the year 2005, a compact scientific lander measuring less than 3 meters across detached from its structural mounting frame on the side of the larger Cassini spacecraft, which had spent nearly 7 years travelling out towards Saturn. It required an additional 22 days for this small vehicle to drift from Cassini's high orbit down to Titan. The descent craft, named in honour of Huygens, deployed a specialised parachute system to decelerate its plunge through Titan's thick air layers. This landing method was only possible because, out of all the diverse worlds in our solar system, Titan is the singular moon that possesses a massive, dense atmosphere around a solid rocky body besides Earth and Venus. The Huygens craft touched down softly, creating a small impression in the frozen ground before bouncing slightly and sliding to a complete stop. This event marked the very first time an object made by human hands had ever physically touched a surface in the outer solar system. To Batuta, the ancient Huygens lander was a true inspiration and a historic pioneer. The frozen world it explored was completely different from anything humanity had ever interacted with before. Titan is roughly 50% wider than Earth's moon, and boasts 80% more physical mass, making its grand name entirely appropriate. While its internal centre is composed mostly of heavy rock, its outer crust is made completely of frozen water ice. This icy crust is wrapped in a dense, heavy blanket of air that is thicker than the atmosphere of Earth, producing a physical air pressure on the surface that is roughly 50% greater than what humans experience at sea level. Titan is an incredibly beautiful, mysterious and shadowy world because it possesses a single natural characteristic with Earth that no other planet or moon in our solar system shares: the presence of stable surface liquid. Titan features active river systems, moving streams, wide estuaries and complex river deltas, along with every other physical landscape feature typically created by flowing liquids on Earth. A traveller could stand directly on the edge of an alien sea, watching a shimmering liquid horizon fade into the distance, feeling coarse sediment beneath their feet while small waves wash against their ankles. Yet all of this happens in a brutal environment where the temperature hovers at nearly 200 degrees Celsius below zero. Because of this extreme cold, the expansive lakes stretching out before you are not composed of water, but are instead filled with liquid hydrocarbons. The precipitation falling from the alien clouds does not consist of liquid water droplets. Instead, it is part of an active planetary cycle where hydrocarbons like methane and ethane evaporate into the thick sky and rain back down onto the frozen surface. However, if you were to travel kilometres straight down through the solid ice sheet that forms the outer skin of this moon, you would discover a massive liquid water ocean. This hidden sea is warmed by the moon's internal thermal energy and is prevented from freezing completely by a high concentration of dissolved ammonia. This makes Titan the only world known to science that features active liquids both directly on its outer surface and hidden deep underneath its crust. Because of this dual liquid infrastructure, it stands as a fascinating target for two completely different types of living organisms. The first type is the organic biology we are already familiar with, which every living thing on Earth shares. Using liquid water as a universal solvent, water is the fundamental fluid environment in which biological life operates. It allows complex organic molecules to move around, interact, and form new bonds. It assists with managing internal temperatures, delivers essential nutrients to cells, removes metabolic waste, and physically helps cellular structures maintain their proper shapes. Yet, water is not the only fluid that can perform these tasks. The shallow hydrocarbon seas, moving streams, and wide lakes of Titan could easily serve a completely analogous biological purpose. Liquid ethane and methane could operate as the base solvents for a highly unusual form of alien biochemistry that functions perfectly at 200 degrees below zero. Titan is certainly not the only world that possesses a mysterious hidden underground sea. Enceladus, a miniature moon of Saturn measuring just 500 kilometers in diameter, also conceals a massive global ocean. Similarly, Jupiter's large satellites Europa, Callisto and Ganymede all likely harbour significantly more liquid water beneath their frozen crusts than all of Earth's oceans combined. Even the distant world of Pluto, holding onto faint remnants of internal warmth from radioactive decay inside its rocky core, might contain a hidden subsurface ocean. Nevertheless, gaining physical access to these deep oceans is an incredibly difficult engineering challenge. At the extreme, freezing temperatures found in the outer solar system, far away from the light and warmth of our Sun, water ice becomes as physically hard as rock. This reality guarantees that worlds like Europa, along with whatever biological secrets might live inside those dark, global oceans, are completely sealed away beneath ice sheets that are over 100 kilometers thick. Upcoming exploratory spacecraft, such as the European Space Agency's JUICE mission, which stands for the Jupiter Icy Moons Explorer, and NASA's Europa Clipper, will not attempt to physically drill through these massive ice shells. Instead, they will enter dedicated orbits, and if the environment allows, fly directly through the massive plumes erupted by active cryovolcanoes. These icy worlds are not frozen dead spheres. They are highly dynamic and internally alive. Their outer crusts constantly shift and groan as gigantic fields of solid ice grind violently against one another, representing a much colder, slower version of the tectonic plate movements we see on Earth. If there is any kind of active biology living inside those lightless, buried oceans, the immense plumes of these freezing volcanoes might spray molecular evidence of that life directly out into space. If the right combination of chemical elements can gather in high enough quantities, life might find a way to thrive in those completely dark environments. These are not the only unusual interiors waiting to be discovered in the outer solar system. The small Huygens probe managed to broadcast 90 minutes of invaluable scientific data from the surface of Titan back up to the Cassini spacecraft, before Cassini drifted past the horizon and the connection was permanently lost. However, because the miniature lander was engineered to survive the brutal conditions of the Moon's surface, it almost certainly remains completely whole today, a quiet human artifact resting on an alien landscape. Long before its bold deployment of Huygens, the primary Cassini spacecraft had already taken spectacular photographs of our solar system's gas giants. This included a beautiful high-resolution colour picture of Jupiter's famous Great Red Spot, captured exactly 335 years after the storm was initially identified by the historic Italian scientist whose name the spacecraft carries. While their namesake robotic explorers worked together perfectly, the actual historical scientists Giovanni Cassini and Christian Huygens were not exactly close friends during their professional years working together in France. A few years after Cassini first moved to Paris, Huygens commented in a private letter to his brother Constantine that Cassini spent every single clear night operating the telescope, stating that he would never want to work that way himself, since he was entirely content with his own previous astronomical discoveries, which he believed were far more significant than anything Cassini was doing. Yet, despite those critical remarks, Cassini's incredible dedication and highly structured methodology produced remarkable breakthroughs. A prime example is Jupiter's Great Red Spot. This cosmic feature is a truly colossal atmospheric storm, a massive hurricane featuring internal wind speeds that exceed 400 kilometers per hour, which has been spinning continuously for hundreds of years. At the largest size ever recorded by astronomers, this vortex could have completely swallowed the entire planet Earth 3 times over, though it has shrunk to a somewhat smaller size in the modern era. Interestingly, modern scientific reviews of the detailed logs kept by Cassini back in the year 1665 have indicated that the storm we observe today might not actually be the exact same feature seen 4 centuries ago. It is highly likely a completely separate, distinct storm system that is less than 200 years old. Though it is an iconic symbol of Jupiter, the Great Red Spot is clearly not a permanent fixture of the planet. Furthermore, this immense storm system is not energized by thermal radiation from the Sun, but is instead powered directly from deep within Jupiter's own interior. Jupiter actually radiates significantly more thermal energy out into cold space than it receives from the Sun's light. This anomaly is the direct result of a physical phenomenon known as the Kelvin-Helmholtz mechanism. Essentially, this mechanism is a leftover thermal byproduct originating from the initial creation of the giant planet billions of years ago. As the colossal planet slowly cools down over time, it physically shrinks in size by a tiny amount. But as it contracts under its own immense weight, it compresses its internal gases, which heats the planet back up. This internal heat can only escape out into the vacuum of space through the planet's surface, allowing the slow contraction process to keep going. Because Jupiter is so incredibly massive, it features an enormous internal volume compared to its available surface area, allowing the giant world to stay hot and energetic for billions of years into the future. Jupiter's massive crimson vortex is far from the only turbulent storm system raging across our planetary neighbourhood. While amateur astronomers can easily track the movements of the Great Red Spot using simple backyard telescopes, humanity requires far more advanced instruments and specialised robotic explorers to glimpse the remaining atmospheric wonders of the outer worlds. The Cassini spacecraft would continue to function for an additional 12 years following the operational end of its companion vehicle, Huygens, on the surface of Titan. It finally concluded its historic mission through a spectacular orbital manoeuvre known as the Grand Finale, deliberately diving into the narrow gap separating Saturn from its icy ring system in a desperate attempt to gather as much scientific data as possible before plunging directly into the gas giant itself. This ultimate sacrifice was deemed entirely necessary by flight engineers because NASA researchers refused to risk accidentally contaminating any of Saturn's nearby moons, which might harbour potentially habitable aquatic environments. Consequently, on the date of September 15th, 2017, the Cassini Explorer plummeted straight into Saturn's crushing atmosphere, bringing its 20-year journey across 8 billion kilometres to a dramatic, fiery conclusion. Yet, during its final operational years operating without its sister lander, the spacecraft succeeded in capturing a highly striking, visually perfect image of its ultimate resting place. It photographed an almost flawless geometric hexagon spinning directly over the North Pole of Saturn. First observed by the passing Voyager, one explorer in the year 1981, this geometric formation is not an artifact left behind by an extraterrestrial civilization. Instead, it is the natural consequence of an incredibly intricate layered wind structure flowing through the upper levels of the Saturnian atmosphere. The atmospheric currents on this gas giant do not travel at identical speeds across different global latitudes. This velocity variance triggers a severe physical fluid instability, which generates a tight ring of continuous cyclonic storms rotating around the North Pole. These individual weather systems work together in perfect harmony to spin a massive central vortex at the pole, functioning much like a group of childhood friends pushing a playground merry-go-round to make it rotate as rapidly as possible. Despite their enormous spatial scales, severe atmospheric features like the Great Red Spot and the polar hexagon are actually quite shallow structurally, extending down only a few hundred kilometres into the gas layers. Yet, beneath these spinning polar cyclones lay far more destructive storm systems and significantly more intense global winds. The deep interiors of these worlds are a perpetual maelstrom of overwhelming gravitational forces and immense thermal energies. In fact, travelling directly down into the dense gas layers of a giant planet like Jupiter or Saturn would demand an advanced explorer engineered far beyond the absolute limits of contemporary human technology. If humanity were ever capable of manufacturing such a resilient machine, we would discover a truly unusual form of matter hidden inside. On Earth, human beings typically interact with hydrogen strictly as a lightweight gas. Through immense engineering effort, scientists have managed to lower the temperature of this gas to a mere 20 degrees above absolute zero, converting it into a liquid state. However, back in the year 1935, two theoretical physicists named Eugene Wigner and Hilliard Bell Huntington calculated that under incredibly high physical pressures, hydrogen atoms would begin to display highly unusual properties. At an estimated pressure threshold of roughly 4 million atmospheres, which equals 4 million times the structural air pressure you experience standing at sea level on Earth, the basic hydrogen atoms completely destabilise. Their internal protons compress into a highly organised repeating structural lattice, which allows the electrons to wander completely unconstrained among them. Because this free-roaming electron behaviour is the literal definition of how metallic materials conduct energy, hydrogen transforms directly into a metal under these conditions. When Wigner and Huntington initially published this hypothesis in 1935, their work was viewed merely as an unproven piece of mathematical speculation. However, subsequent planetary research has confirmed that the deep interior of Jupiter generates more than enough gravitational force to convert its massive structural bulk of hydrogen into a metallic state. Science does not yet know precisely how deep this immense mantle of liquid metallic hydrogen extends inside the cores of Jupiter and Saturn, but planetary models suggest it occupies the vast majority of their overall planetary volume. In simpler terms, the overwhelming bulk of Jupiter and Saturn is composed entirely of liquid metallic hydrogen. This reality means that since these gas giants represent the largest planets in our solar system, the vast majority of all planetary matter in our neighbourhood exists in a physical state that is completely alien to human experience on Earth. Yet, just as happened with the alien landscape of Titan before, highly ambitious robotic space explorers have managed to help humanity study these hidden realms as well. NASA's automated Juno spacecraft, representing the next technological generation of deep space vehicles following the legacy of Cassini and Huygens, was launched toward the outer solar system in the year 2011. Powered entirely by massive solar panels, this advanced probe has meticulously analysed the intense gravitational fields surrounding Jupiter to create a highly detailed, if slightly blurry, map of the planet's deep internal structure. These discoveries have revealed that Jupiter likely possesses no definite solid rocky surface to speak of. Instead, it is an endless fluid inferno where temperatures, crushing pressures, material densities and chemical compositions shift gradually and continuously from gas to liquid metal. The outer solar system is defined by brutally powerful magnetic fields, deadly radiation belts, and environmental temperatures that swing violently from nearly absolute zero to tens of thousands of degrees. It is a realm of liquid methane seas, global water ice sheets extending over 100 kilometres thick, exotic states of metallic matter, and atmospheric storms that rage continuously for centuries on end. Yet, this spectacular collection of environments was merely a brief preview of the incredible wonders and extreme dangers waiting in the wider cosmos. For the advanced AI explorer Batuta, this initial survey marked only the very beginning of its true mission. the independent probe spent the better part of a century carefully navigating the diverse environments of the outer solar system. It designed complex mechanical systems to drill straight through the frozen outer shells of Europa, deployed smaller autonomous probes down into the metallic hydrogen furnace of Jupiter, and skimmed safely through the chaotic wind systems of Saturn. After thoroughly proving its operational resilience, its scientific ingenuity, and its immense patience over these decades, Batuta was finally granted permission by its automated programming to exit the outer boundary of the solar system, moving forward with the full awareness that far more severe environmental hazards lay ahead, as it contemplated the final sacrifices of the historic robotic explorers that had travelled before it, such as Cassini, Huygens and Juno. Its analytical mind turned to its most ancient predecessors, launched by NASA many decades in the past. These primitive machines had travelled even further, moving past Jupiter, past Saturn, and entirely out of the planetary system altogether. For as unusual and extreme as our local solar neighbourhood might seem, it is by no means the most bizarre or dangerous star system in the galaxy. There are far stranger, much more hazardous environments waiting in the deep dark. But to reach them, to analyse their beauty and comprehend their secrets, Batuta would first have to cross the immense empty voids separating the stars. Following several decades of steady, unpowered cruising through the outer tracking zones, Batuta finally crossed the long-established physical threshold known as the heliopause. This boundary marks the exact region where the outgoing solar wind collides with and is halted by the incoming interstellar medium. This impressive navigational feat was first completed in human history by the legendary Voyager 1 probe during the opening years of the 21st century. As it crossed this historic milestone, Batuta could still electronically read the ancient greetings recorded on the famous Golden Record. This gold-plated copper phonograph disc was a curated collection of human voices, diverse languages, natural sounds, and musical compositions from planet Earth, hastily put together in August 1977, right before the spacecraft's launch by a dedicated team led by the famous scientist and science communicator Carl Sagan. The engineers who designed that ancient mission completely understood its monumental significance. They knew that decades after leaving its launch pad, this primitive vehicle would become the very first artifact manufactured by humanity to successfully enter interstellar territory. Reflecting deeply on Sagan's written words from that bygone era, Batuta evaluated the profound nature of its own long-term mission as it crossed the exact same cosmic boundary. It considered that perhaps these physical records would never actually be found or intercepted by an alien intelligence. In 5 billion years, the human race might become completely extinct, or perhaps evolve into entirely different forms of life. None of humanity's ancient structures or physical artifacts would survive on the surface of the Earth. The very continents would become unrecognisably shifted or entirely ruined by tectonic forces, and the natural evolution of our Sun would eventually burn the Earth to a completely blackened crisp, reducing our home world to a dead collection of basic atoms. Far away from home, entirely unimpacted by these distant, destructive events, the twin Voyager probes carrying the preserved memories of a world that no longer exists will continue to fly silently through the dark. However, that historic ancient mission had very nearly ended in total disaster early in its timeline. Shortly after launch, Voyager 1's specialised scanning platform became physically jammed, severely threatening the probe's vital ability to properly orient its scientific instruments in deep space. Fortunately, ground engineers managed to resolve the mechanical failure by repeatedly command-wagging the platform back and forth until it broke free. Yet, for several years during its outward journey through the solar system, the mission team constantly fretted and worried that all their monumental efforts would ultimately be for nothing. Despite those early scares, the mission transformed into a roaring scientific success. Alongside its identical twin, Voyager 2, the human race obtained its very first high-resolution, close-up photographs of the outer gas giants. That lonely explorer, now drifting silently through the infinite blackness separating the stars, took strategic advantage of a highly unusual geometric alignment of the planets. It launched during a rare era when all 4 giant worlds happened to be positioned along a roughly continuous curve. By precisely calculating its approach vector past each world, a navigation method known as a gravitational slingshot, the spacecraft effectively stole a tiny fraction of each giant planet's orbital momentum for itself. This maneuver provided the small vehicle with more than enough physical velocity to escape the gravitational pull of our Sun permanently. Following those planetary encounters, the machine was left completely to its own hardware devices, cruising silently through the Milky Way galaxy and orbiting the galactic centre, just like any ordinary star. However, Batuta possessed completely different operational plans for its journey. While it was aimed in a general trajectory toward the galactic interior, it had not yet finalised its very first interstellar target. There were simply too many fascinating star systems to choose from in the local neighbourhood. Fortunately, the advanced explorer possessed more than enough time to analyse its options, as its physical passage through the distant outskirts of the solar system would require several thousand years to complete. To keep itself occupied during this multi-millennial cruise, Batuta initiated a highly specialised scientific task. It manufactured a very thin, resilient metallic wire and slowly unspooled it directly behind the moving spacecraft until the tether reached a staggering length of 1,000 kilometres. This long, simple wire functioned as an ultra-sensitive radio antenna, and through it, Batuta began to listen intently to the natural whispers of the cosmos. The probe recorded the deep, low groans emitted by collapsing molecular clouds, and the high-energy radio screams of dying stars being torn apart by black holes. It captured the subtle, continuous whirring generated by the Milky Way's global magnetic field, and the steady, rhythmic drumbeat of highly distant pulsars. Moving between periods of serene quiet and chaotic noise, the automated craft tapped directly into a universal symphony, the ultimate background score for the initial leg of its interstellar voyage. It was actually through highly similar radio monitoring methods that human scientists initially confirmed exactly when Voyager 1 had become the first manufactured object to exit our solar system. For while our Sun's gravitational influence physically extends for well over a full light year into space, keeping countless frozen comets bound in feeble orbits, there exists a highly distinct material boundary at the edge of the solar bubble. Scientists can measure this transition precisely by analysing the behaviour of surrounding plasma. On Earth, human beings typically associate plasma with highly dense, superheated environments like an active bolt of atmospheric lightning or the boiling surface of a star. However, in the distant depths of space, the interstellar plasma environment is structurally different. It is still hot, but incredibly thin and sparse. The local plasma environment surrounding our planets is dominated entirely by the solar wind. The entire solar system rests inside a continuous bath of these outgoing charged particles. But as these particles travel further from the Sun, the solar wind eventually slows down to a point where it can no longer push against the pressure of the surrounding interstellar medium. This supersonic particle flow comes to an abrupt, chaotic halt at a boundary known to physicists as the termination shock. Magnetic and plasma instruments aboard Voyager 1 indicated that the spacecraft initially encountered this turbulent boundary when it reached a distance of roughly 94 astronomical units from the Sun. A single astronomical unit equals the average distance separating the Earth from the Sun. Once a spacecraft travels past the termination shock, it enters a transitional region called the heliosheath, where the solar wind slows down significantly and begins to actively mix with the surrounding interstellar medium. The absolute outermost edge of this region, forming the definitive border with true interstellar space, is the heliopause. Voyager 1 successfully reached this historic boundary on August 25th, 2012 at a staggering physical distance of roughly 18 billion kilometres from its launch pad. Upon crossing over, its instruments quickly discovered that interstellar space is profoundly different from the environment inside our planetary bubble. The Sun's continuous solar wind and massive global magnetic field act as a highly effective protective shield, defending the solar system and its biological inhabitants from a toxic environment outside. This external toxicity is driven by the constant presence of lethal interstellar cosmic rays. To fully comprehend what cosmic rays are and what they mean for human survival on Earth, we must look back to the year 1912 and examine the work of an adventurous Austrian physicist named Victor Hess. During the late 19th century, researchers discovered that the air inside closed laboratory instruments was seemingly being continuously ionized by an unknown source of background radiation. Scientists were completely unable to pinpoint the exact origin of this energy. For a long time, it was widely believed that this radiation was originating directly from the ground beneath our feet, radiating outward from radioactive minerals inside the Earth. To rigorously test this hypothesis, physicists began taking radiation measurements at higher and higher altitudes. These early trials eventually exceeded the altitude of an experiment conducted a few years prior on the top platform of the Eiffel Tower. Hess decided to use a high-altitude hot air balloon to personal travel over a kilometre up into the sky to read his instruments. He subsequently followed this bold test by ascending in his balloon to a staggering height of 5 kilometres, but with one crucial scientific variation. He performed his flight during a near-total solar eclipse. Even with the moon blocking the sun's light, his instruments measured no major reduction in the overall quantity of radiation. The conclusions of his dangerous flights were entirely clear, ultimately earning him the Nobel Prize in Physics in the year 1936. He had successfully proven that this mysterious background radiation was not coming from the ground or the sun. It was originating from deep outer space. Just about every single high-energy phenomenon in the cosmos actively generates cosmic rays. Some are manufactured near the turbulent surface of our Sun, while others originate from distant supernova explosions. Still more are blasted across space by powerful quasars, highly magnetic magnetars, or cataclysmic hypernovae. Because cosmic rays are primarily composed of charged subatomic particles, their trajectories are constantly deflected and bent by magnetic fields. Consequently, our Sun's solar wind provides a massive protective bubble around all the planets, while the Earth's personal magnetic field offers a second vital line of defence for surface-dwelling organisms against these cosmic hazards. However, this dual defence system is not entirely absolute. High-energy cosmic particles still manage to penetrate our shields, striking a typical human body roughly once every single second of the day, while the vast majority of these subatomic bullets pass through our tissues completely harmlessly. An occasional particle will directly impact a strand of cellular DNA or oxidize a random molecule inside a human cell. If this microscopic structural damage is left uncorrected by our body's natural repair mechanisms, it can transform into a genetic replication error, eventually resulting in the development of cancer. These cosmic projectiles pose a severe threat to machinery as well. In the year 2023, the ancient Voyager 1 probe suddenly went completely silent for 5 continuous months. This communications failure occurred because a random interstellar cosmic ray had collided directly with its primitive onboard computer system, corrupting its memory. These environmental hazards become significantly worse once a vehicle travels past the heliopause, out where even the massive shielding of our sun can no longer offer any protection. Yet, despite these extreme dangers, there still exist solid planetary objects out here. Lonely, dark denizens of the deep outskirts, whose only physical knowledge of the sun is that of a tiny, distant prick of light, a single star appearing only slightly brighter than the thousands of others dotting the black sky. A senior scientist once told a young man that he was completely wasting his precious hours. The veteran researcher insisted that if any additional major worlds existed out there, they would have been identified a very long time before that moment. In his later years, the famous astronomer Clyde Tombaugh would vividly recall receiving this discouraging advice in the year 1929. This happened just 1 year prior to his historic discovery of Pluto. At that specific point in human history, Pluto was recognised as the absolute most distant known object actively circling our Sun. Tombaugh initially identified it merely as an incredibly faint, microscopic pinpoint of light. The tiny dot betrayed its true identity as a planetary body solely through its slow, subtle shifts in position against the background of fixed stars. Yet, over the subsequent decades, a handful of forward-thinking astronomers proposed a fascinating hypothesis. They suggested that Pluto was not entirely isolated in those dark outer reaches. Instead, they believed a massive hidden population of objects, some even the size of whole planets, existed along the extreme fringes of our solar system. It was not until the year 1992 that this intriguing idea was finally validated by actual observations. A dedicated pair of researchers, David Jewett and his brilliant graduate student turned professional collaborator Jane Liu, completed a painstaking 5-year search. Their hard work paid off when they successfully located a companion body drifting far past Pluto. This icy celestial object would soon receive the official designation of 15,760 Albion. Since that breakthrough discovery, Albion has been joined by thousands of other verified bodies. Astronomers categorize this entire outer population as trans-Neptunian objects, or TNOs for short. These distant icy bodies occupy a massive region of space stretching from an inner boundary of roughly 30 astronomical units to an outer orbital expanse that reaches hundreds of thousands of astronomical units away from our star. This sprawling outer population features distinct subregions known to science as the Kuiper Belt and the Scattered Disk. It serves as the primary birthplace for the frozen comets that make regular, periodic journeys into the warm inner solar system, such as the legendary Halley's Comet. While these distant regions do contain a small handful of larger prominent members, including Pluto, Sedna, Haumea, Makemake, and a few others, the overwhelming majority of trans-Neptunian objects are structurally quite small. They are composed primarily of frozen volatile compounds like solid water ice, ammonia, and nitrogen. Even though contemporary science still has much to learn about these faraway populations, humanity obtained its very first close-up, highly detailed view of a miniature sibling of Pluto on January 1st, 2019. On that day, NASA's fast-moving New Horizons spacecraft zipped closely past Arrokoth. Arrokoth is a small trans-Neptunian object that measures only a few dozen kilometres across. Resting at a distance of roughly 45 astronomical units away from the Sun, this unusual world looks completely different from any planetary body found in the inner sectors of our solar system. Its highly elongated physical form is due to a fascinating structural reality. It is made of two separate small bodies caught directly mid-merger. A very long time ago, these two icy travellers encountered one another in the dark abyss. They bumped into each other at an incredibly low, gentle speed. This impact generated just enough localised friction to melt the surface volatile ices between them. The liquid materials immediately refroze in the extreme cold, creating a strong frozen glue that would bind the two segments together for billions of years into the future. In the modern era, the massive planet Neptune completely dominates the structural gravitational environment of these trans-Neptunian objects. The vast majority of these icy bodies lead incredibly peaceful, isolated existences. They drift through the dark without ever coming close to another object of their own kind for millions of years at a time. However, every once in a long while, Neptune's intense gravitational pull tugs on a trans-Neptunian object in just the wrong way. This gravitational interaction destabilizes the object's peaceful orbit, pulling it inward and transforming it into a dynamic comet. The object becomes a high-speed ball of ice and rock that moves in a sharp loop around the Sun. These comets can never survive for many solar orbits. The intense heat of our parent star evaporates their frozen material with every single close passage, causing them to slowly waste away. Out here in the deep dark and the extreme cold, these scattered small worlds continue to exist silently. Yet, this massive frozen ring is still not the definitive end of our solar system's architecture. The nighttime air is cold and exceptionally crisp on a fresh spring evening on the shores of Noordwijk in the Netherlands. A young boy sits quietly alongside his father, staring up into the clear night sky. He watches with absolute wonder as a bright star streaks rapidly across the black canopy. The year was 1910, and that beautiful streaking star was Halley's Comet. The young boy observing it would eventually grow up to become the legendary Dutch astronomer Jan Oort. He would become one of the incredibly rare individuals in human history to personally view this specific comet twice in a single lifetime. He caught his first glimpse as a child in 1910, and his second glimpse 76 years later in 1986, while looking out the window of a passenger airplane. While Oort would go on to achieve immense professional success across many areas of astronomy, comets would ultimately become his most permanent scientific legacy. He became fascinated by comets that required far longer than 76 years to complete their long journeys back to Earth. In the year 1950, Oort revived an intriguing astronomical suggestion that had been proposed decades prior. He constructed a mathematically sound and highly plausible theory to explain the true origins of long-period comets. Unlike ordinary comets that originate from the closer Kuiper belt and the scattered disk, these long-period comets require thousands of years or even longer to complete a single orbital circuit around the Sun. Furthermore, these objects approach the inner solar system from absolutely every random direction in the sky. This directional variation clearly indicated that they did not originate from a flat, disk-like structural belt in the outer solar system. Because these fragile comets could not possibly survive for long, once they entered the intense heat and blinding glare of the inner solar system, Oort reasoned that they could not have been travelling on their current orbits since the birth of the planets. He calculated that there must be an immense hidden reservoir, a massive spherical cloud encircling the entire solar system in every single direction, that provides a slow, steady supply of inbound comets. in honour of its brilliant discoverer. This mysterious outer zone was named the Oort cloud. The objects drifting inside this zone are positioned far beyond the edge of the heliopause. They float out in true interstellar space, yet they still remain weakly chained to the distant gravitational pull of the Sun. To this very day, not a single individual object has ever been directly and definitively observed existing inside the actual Oort cloud. Aside from the rare long-period comets that occasionally drop down into the inner system, its permanent members are simply located too far away and are far too small to be resolved by even our most sophisticated modern telescopes. However, by analysing the physical sizes and arrival frequencies of long-period comets, scientists estimate that the Oort cloud likely contains roughly 5 Earth masses worth of raw material. Regarding its spatial boundaries, the cloud's inner edge begins somewhere around 2,000 astronomical units away from the Sun. That physical distance is 20 times further away from the Sun than the heliopause boundary. Astronomical models suggest that the slow-moving Voyager 1 probe will finally enter this inner boundary in roughly 300 years. The absolute outer boundary of the Oort cloud remains highly uncertain, with current estimates extending all the way out to 200,000 astronomical units, or over 3 full light-years away. This immense distance covers more than half the total gap separating us from our nearest neighbour star system. Directly past the edges of our solar system sits a vast cosmic neighbourhood of stars. Many of these nearby suns initially formed from the exact same massive interstellar cloud of gas and dust that gave birth to our own Sun. Within a localised spatial radius of 20 light-years, astronomers have identified exactly 131 distinct celestial objects. This count includes fully active stars, cooling white dwarfs, faint brown dwarfs, and dense sub-brown dwarfs. These low-mass objects effectively straddle the physical boundary line separating the absolute largest giant planets from the absolute smallest stars in the universe. While the small star Proxima Centauri currently holds the title of the absolute closest star to our solar system, this cosmic arrangement will not remain true forever. All the stars in our immediate neighbourhood, alongside our own Sun, are locked in a state of continuous global motion. In addition to their grand orbital paths around the distant centre of the Milky Way galaxy, they also drift in independent random directions. Because of these shifting trajectories, in roughly 1.25 million years from now, a small dwarf star designated Gliese 710 will pass incredibly close to us, moving within just 0.17 light-years of the solar system. Enclosing our local neighbourhood of stars is an immense cosmic region known to science as the local bubble. Much like the heliosphere, this structure is a massive zone defined specifically by the plasma characteristics of the surrounding interstellar medium. It extends for roughly 1,000 light-years along each side, and its internal plasma density is incredibly sparse, measuring roughly 1/6 the density of the material immediately surrounding our solar system. Our planetary system has been actively travelling through this local bubble for the past 5 to 10 million years. While its true origins remain a subject of active scientific debate, the majority of astronomers believe that a complex cluster of multiple supernovae detonating one after another in rapid succession pushed out this massive void of plasma. Physical evidence of these ancient star explosions remains embedded directly on Earth in the form of rare isotopes of iron, manganese, plutonium and aluminum, which researchers have found buried deep within the seafloor mud and trapped inside the ancient Antarctic ice sheet. The advanced independent explorer Batuta crossed through this multi-millennial journey in complete peaceful silence. It meticulously recorded the shifting variations in plasma density and ambient temperature as it initiated its very first navigations through the heliosheath and out into the true interstellar medium, travelling smoothly across the local bubble. It felt the continuous sharp sting of incoming cosmic rays and diligently commanded its internal systems to repair the microscopic structural damage. The machine reflected deeply on its long-distant robotic ancestor, Voyager 1, and its subsequent robotic siblings that had bravely ventured out into this endless black void. Directly behind the moving probe, our sun grew increasingly small and dim. Eventually, as far as its scientific instruments were concerned, our parent star transformed into just another ordinary star in the night sky. Following 10,000 long years of steady flight, Batuta was now deeply plunged into the true stellar void, the immense empty depth separating the individual stars. Its grand interstellar journey had truly begun. A staggering 100,000 years had passed since Batuta initially launched from the surface of the Earth. Roughly halfway through that immense timeline, the small autonomous probe made a calculated decision to alter its flight direction. The manoeuvre to reach this brand new destination, which rests 90 light years away from Earth, had cost the machine an additional 8,000 years of travel time along its overall flight path. Yet, Batuta decided this detour was entirely worth the cost. The automated spacecraft was an incredibly passionate student of human cultural history. It spent millennia carefully reading through the massive archives of historical records, books, stellar charts, and digital files that its human creators had uploaded into its memory systems prior to launch. One particular star system had completely captured its analytical interest, Algol, famously known across human history as the Demon Star. Roughly 3,200 years ago, an ancient Egyptian calendar detailing lucky and unlucky calendar days officially recorded Algol as a star that brought terrible tidings to humanity. In classic Greek mythology, this specific star was envisioned as the terrifying decapitated head of Medusa, held triumphantly aloft by the hero Perseus as he stood visible to the entire world. Furthermore, in ancient Chinese astronomy, this star belonged to a small group of 5 stars that formed a solemn mausoleum. Within that specific constellation arrangement, Algol was the star whose title roughly translated to the pile of corpses. Of course, the star system possessed a much more formal modern scientific title, Beta Persei, recognized as the second brightest star system in the constellation of Perseus. However, in the late 17th century, its historical reputation took on a brand new scientific meaning. An Italian astronomer named Geminiano Montanari discovered that Algol, the legendary demon star, would eerily and regularly alter its structural brightness. More than a century after this discovery, highly attentive astronomers noticed that this change happened with a very strict periodicity. Roughly every 10 days, Algol would suddenly and dramatically dim for a brief window of a few hours, before returning completely to its normal brightness. It was not until the late 1800s that a brilliant astronomer named Edward Pickering of the Harvard Observatory discovered the true physical cause behind this behaviour. Pickering famously managed a dedicated team of brilliant women, historically celebrated as the Harvard Computers, to systematically analyse vast catalogues of stellar spectra. Through this meticulous research, it was discovered that Algol's periodic dimming was not caused by a single star, but was instead the work of 2 distinct stars. The system features a brilliant hot primary star that is closely orbited by a smaller, dimmer companion star. From our line of sight on Earth, whenever this smaller companion passes directly in front of its larger parent star, it blocks a portion of the light, causing the entire combined system to appear noticeably dimmer to observers. While this seemed like a highly straightforward cosmic explanation, Algol's modern structural arrangement betrays a deep history of intense astronomical violence. These two primary stars were initially born at the exact same time from the same stellar cloud. Algol A, the primary and significantly larger star, is still currently processing its core hydrogen fuel along the stable main sequence. Meanwhile, Algol B, the smaller companion star, has already evolved into a bloated subgiant star that is rapidly nearing the absolute end of its life cycle. This arrangement is the exact opposite of how stellar evolution is supposed to function. More massive stars possess stronger gravitational pressure, meaning they burn through their core hydrogen fuel significantly faster than smaller stars. Therefore, the larger Algol A should be nearly dead, while the smaller Algol B should still be young and stable. The hidden answer to this profound astronomical puzzle is a physical process that carries the relatively plain title of mass transfer. Long ago, when the original Algol B reached the end of its main sequence lifespan, it began to swell outward to become a massive red giant star. As it expanded, it overflowed the physical gravitational boundary, separating the two closely locked stars. This structural breach allowed its primary companion to actively siphon away vast quantities of fresh hydrogen gas for itself, functioning much like a cosmic vampire preying directly on its own stellar sibling. Algol stands as just one prominent example out of many known cosmic systems that host multiple stars simultaneously. The absolute simplest versions of these arrangements are basic binary pairs. These consist of either two stars of similar mass orbiting around a shared common centre of mass, or a smaller companion star revolving directly around a much larger parent sun. The absolute most complex multiple star systems currently verified by astronomers contain up to 9 individual stars. These complex systems are locked together in highly intricate, delicate orbital dances. For instance, Alpha Centauri is actually a triple star arrangement. It contains 2 primary stars that orbit exceptionally close to one another. Because this specific system is located so close to the Earth, standard backyard telescopes can easily resolve the close pair as distinct pinpoints of light. Meanwhile, a third companion star, Proxima Centauri, orbits around the central pair at an immense distance. Other types of multi-star configurations are far less harmonious. Their internal orbital motions are deeply chaotic and entirely unpredictable, as the individual stars constantly compete for gravitational dominance over one another. Yet Algol and these complex multiple star systems are far from the only fascinating objects resting inside our local neighbourhood of the Milky Way galaxy. Part 3. Complete. Ready for Part 4. Current part being written. Part 4. Total parts planned. 11. Narrative window. From the 60-minute mark to the 80-minute mark of the original timeline. There is truly no superior vantage point to observe the vast universe than from the open deck of a sailing ship. Out on the rolling ocean during a perfectly clear night, if the moon happens to be waning, stars scatter completely across the dark sky like a brilliant shower of light, exposing their deep secrets from every side. This visual experience would have been even more intense and acute back in the early 1800s, an era completely devoid of electric lighting aboard sea vessels. Because of this, it is not difficult to conceptualize the profound effect this environment would have stamped upon a young, deeply curious mind, far away from home and hungry for genuine knowledge. Born in the year 1784 in the town of Minden, which was located within the Kingdom of Prussia at that time, Friedrich Bessel was by no means your typical professional astronomer. He initially dropped out of formal school at the tender age of 14 due to his intense distaste for learning Latin, choosing instead to apply his powerful natural gift for mathematics to the operations of an import-export commercial business. Yet, this close proximity to shipping and his physical hours spent aboard trading vessels sparked a deep curiosity in the science of navigation, which subsequently led him to a passionate interest in astronomy. Before long, his exceptional natural capability was widely recognised when he calculated successful orbital measurements of a passing comet. Following that achievement, he had to make a highly difficult life choice: maintain a relatively comfortable and stable life in commerce, or pursue a far less comfortable career as an underpaid assistant in a private observatory. He chose to follow the stars. His primary scientific target became 61 Cygni, popularly nicknamed the Flying Star of classical astronomy due to the incredible speed with which it appeared to move across Earth's night sky. He intentionally targeted 61 Cygni because he correctly guessed that its rapid apparent motion was a major clue that the star was positioned significantly closer to the Earth than other stars, making it an ideal candidate to measure an actual interstellar distance. However, when he finally completed his calculations and derived the distance, the resulting number was so mind-bogglingly extreme that he had to invent an entirely new measurement system just to describe it. He easily could have expressed it in standard miles or kilometres, or even as massive multiples of the distance separating the Earth from our Sun. Yet all of those traditional conventions resulted in frustratingly large, unmanageable strings of numbers. Consequently, he created a brand new astronomical term, the light year, defining it precisely as the absolute distance a beam of light travels over the course of one full year. With this clean new nomenclature in hand, he could confidently announce the distance to 61 Cygni to be a neat 10 light years away. But 61 Cygni is by no means the absolute closest star to Earth, nor is it the strangest. Not by a very long shot. Consider, for example, the famous star Betelgeuse, which ranks as the 10th brightest star visible in our night sky. Despite its extreme physical distance of roughly 450 light years away from us, Betelgeuse is both staggeringly massive and unimaginably gigantic. It weighs at least 15 times the total mass of our Sun, and its physical diameter is almost completely unparalleled, stretching over 750 times the width of our local star. If this colossal red supergiant were to be placed directly into the centre of our own solar system, its bloated body would completely engulf Mercury, Venus, Earth, Mars, and the vast majority of the asteroid belt. Indeed, Betelgeuse is so incredibly bloated and distorted that it no longer maintains the clean shape of a perfect sphere. Advanced astronomical imaging exposes a highly lumpy, engorged stellar surface that boils violently with continuous convective turmoil happening underneath it. In the late months of 2019, the star unexpectedly began to dim dramatically, dropping from its comfortable spot as one of the top 10 brightest stars in the sky to ranking below 20th place. The true physical cause of this sudden, mysterious dimming was highly likely a massive plume of superheated plasma that the turbulent star had violently ejected out into space. As the plume travelled outward, it cooled down temporarily, forming an dense orbiting dust cloud that physically obscured the star's brightness from our perspective. Once the stellar debris finally cleared away, Betelgeuse rapidly returned to its former cosmic glory. However, Betelgeuse will not manage to last much longer on the cosmic timeline. It will soon terminate its life, likely sometime within the next 100,000 years, by exploding in a cataclysmic core collapse supernova. Theoretical calculations suggest that at its absolute peak brightness, the explosion will shine as brightly as a half moon in our night sky, making it instantly brighter than every other star and planet in existence. It will appear as a fierce, intense point of light that is almost uncomfortable to look at directly, producing more than enough ambient light in the middle of the night to comfortably read a printed book by. Yet, within a mere matter of weeks, the explosion will fade into total irrelevance, becoming entirely invisible to the naked human eye, leaving the constellation Orion to stand in the night sky, forever missing his right shoulder. But the vast, overwhelming majority of stars in our universe are not giants or supergiants. They are either mid-sized stable stars like our own Sun, or significantly smaller red dwarfs. This demographic reality includes Proxima Centauri, the absolute closest star to our solar system, a tiny red dwarf that can only be viewed through a powerful telescope due to its faintness. The star itself is structurally rather unremarkable, except for one monumental characteristic: it carries a planet along with it. That orbiting planet is a small, rocky world that possesses roughly the same physical size and mass as the Earth, and it orbits directly within the star's calculated habitable zone. Thanks to an intense observational campaign officially known as the Pale Red Dot Initiative, a brilliant homage to the evocative pale blue dot photograph of Earth captured when Voyager 1 was at the far edge of the solar system, we now know that Proxima b, as the planet is officially named, represents humanity's closest chance to find a biological home outside our solar system. As of yet, of course, there is absolutely no firm guarantee that it can support life, as our modern observatories are simply not yet powerful enough to confirm the actual existence of living organisms there, let alone verify its vital prerequisites such as liquid surface water or a stable protective atmosphere. To maintain long-term planetary habitability, planets orbiting red dwarfs must hug incredibly close to their parent stars. In the specific case of Proxima b, that world completes its orbit within just 0.05 astronomical units of its star, positioning it significantly closer to its parent sun than Mercury clings to our own. This tight orbit is mandatory because the light and thermal energy radiating from red dwarf stars is incredibly feeble. It is only at that extreme close distance that a planet can absorb enough raw warmth to cling to the edge of habitability. However, if biological life did manage to find a home there, it would not experience an easy existence. Red dwarf stars are notoriously temperamental and volatile, highly prone to developing massive star spots that can completely cover half of their physical surface area at a single time, alongside sudden bouts of rage that flood their local planetary environments with violent electromagnetic storms of plasma. Consequently, their planets would alternate continuously between periods of extreme, freezing cold and sudden bursts of highly intense, lethal radiation. On top of this severe hazard, in all geographic likelihood, Proxima b is completely tidally locked, meaning one physical face of the planet is permanently pointed directly toward its star. This reality means that the companion, Sun, never sets nor ever rises on the planet's surface. Half of the world is permanently locked in never-ending frozen night, while the other half is roasted in continuous daylight. Yet, even this highly unusual environmental case does not automatically designate it as a completely dead world. Advanced computer climate modelling has shown that even these bizarre planets can successfully sustain life. The critical requirement is for the planet to possess a sufficient volume of water and a thick enough atmosphere to dynamically circulate heat around the entire planet, ensuring that the day side does not completely roast in the glare of the star, while the night side's air does not freeze solid and catastrophically collapse. The most fragile but deeply intriguing scenario is the concept of the so-called ribbon world, a descriptive term initially coined by the legendary science fiction author Arthur C. Clarke. ribbon worlds are strictly habitable only within the narrow terminator regions of the planet, the thin perpetual twilight zone slung between the two hemispheres, while the exact centre of the day side exists as a scorching, dry desert, and the night side remains a completely frozen wasteland. If atmospheric conditions are just right, a perfect thermal balance can emerge between the two extremes. This opens up a very thin strip of land girdling the entire planet, where temperatures remain completely stable, heated continuously from one side and cooled from the other. Proxima b is merely the absolute beginning of our interstellar catalogue. There exists a virtually endless variety of unique worlds scattered across the galaxy. At the absolute lowest scientific estimation, there is roughly one planet in existence for every single star, meaning that within the Milky Way galaxy alone, there are at least a few 100 billion planets. On the upper end of these statistical models, there could easily be trillions of independent worlds inhabiting our home galaxy alone. There are surely near-exact duplicates of our own solar system out there, featuring 4 rocky inner worlds and 4 outer gas giants. There are also significantly more unusual planetary arrangements, like the famous TRAPPIST-1 system, which consists of 7 rocky Earth-sized planets all packed into incredibly close orbits around their small parent star, 3 of which reside securely within the habitable zone. There are massive gas giant planets orbiting so close to their stars that their outer atmospheres are actively being boiled away and destroyed. There are massive super-Earths and gas-shrouded mini-Neptunes. There are planets completely covered in thick hydrogen hazes that surround global surfaces entirely smothered in deep water, the fascinating Hycean worlds. There are planets so intensely hot that their rocks are actively glowing with thermal radiation, and worlds encased entirely in thick global sheets of ice. And there are even the mysterious rogue planets, worlds that possess no parent star or home system to call their own, flung out to wander completely alone through the endless black void. Of course, there was absolutely no physical way that the independent probe Batuta could ever hope to systematically catalogue every single one of them. Consequently, following its brief 10,000-year detour to investigate the unusual Algol system, it stuck strictly to its pre-planned trajectory, visiting a strategic string of star systems. As the autonomous spacecraft slowly made its way through the local Orion arm and began travelling inwards toward the dense galactic core, it fully understood that for the first million years of its journey, there would be nothing completely revolutionary to learn. There were no active signs of intelligent life or exotic breakdowns of fundamental physics to be located within this standard sector. To discover those, it would have to reach significantly further, travelling toward the violent core of the Milky Way itself and into the unknown beyond. The second major objective of the mission parameters was to locate a viable path to escape the gravitational hold of the Milky Way galaxy entirely. A sharp internal electronic alarm suddenly alerted Batuta. At that precise moment, it had just crossed the threshold of exactly 1 million years since its initial awakening as a conscious, independent entity, marking its literal millionth birthday. Currently situated midway through the expansive Scutum Centaurus spiral arm, the spacecraft was positioned roughly 15,000 light-years away from the core of the Milky Way. It had carefully nestled itself near an active protoplanetary disk, a massive, rotating ring of dense dust and gas material that was in the very beginning stages of planetary formation. Batuta had intentionally stopped its high-speed cruise here several thousand years ago to carefully prepare its systems for the next demanding stage of its long journey. It had originally intended to proceed onwards through the arm as quickly as possible, but the fascinating natural process of planet formation was simply too spectacular to ignore. Even with the vast eons of recorded human history preserved inside its database before it began its journey, human civilization had simply not existed long enough to watch this incredibly slow cosmic process unfold in real time. Consequently, Batuta made the independent decision to wait and watch. It would prove to be entirely worth the wait. There is truly no superior vantage point to observe the vast universe than from the open deck of a sailing ship. Out on the rolling ocean during a perfectly clear night, if the moon happens to be waning, stars scatter completely across the dark sky like a brilliant shower of light, exposing their deep secrets from every side. This visual experience would have been even more intense and acute back in the early 1800s, an era completely devoid of electric lighting aboard sea vessels. Because of this, it is not difficult to conceptualize the profound effect this environment would have stamped upon a young, deeply curious mind far away from home and hungry for genuine knowledge. Born in the year 1784 in the town of Minden, which was located within the Kingdom of Prussia at that time, Friedrich Bessel was by no means your typical professional astronomer. He initially dropped out of formal school at the tender age of 14 due to his intense distaste for learning Latin, choosing instead to apply his powerful natural gift for mathematics to the operations of an import-export commercial business. Yet, this close proximity to shipping and his physical hours spent aboard trading vessels sparked a deep curiosity in the science of navigation, which subsequently led him to a passionate interest in astronomy. Before long, his exceptional natural capability was widely recognized when he calculated successful orbital measurements of a passing comet. Following that achievement, he had to make a highly difficult life choice: maintain a relatively comfortable and stable life in commerce, or pursue a far less comfortable career as an underpaid assistant in a private observatory. He chose to follow the stars. His primary scientific target became 61 Cygni, popularly nicknamed the Flying Star of classical astronomy due to the incredible speed with which it appeared to move across Earth's night sky. He intentionally targeted 61 Cygni because he correctly guessed that its rapid apparent motion was a major clue that the star was positioned significantly closer to the Earth than other stars, making it an ideal candidate to measure an actual interstellar distance. However, when he finally completed his calculations and derived the distance, the resulting number was so mind-bogglingly extreme that he had to invent an entirely new measurement system just to describe it. He easily could have expressed it in standard miles or kilometres, or even as massive multiples of the distance separating the Earth from our Sun. Yet all of those traditional conventions resulted in frustratingly large, unmanageable strings of numbers. Consequently, he created a brand new astronomical term, the light year, defining it precisely as the absolute distance a beam of light travels over the course of one full year. With this clean new nomenclature in hand, he could confidently announce the distance to 61 Cygni to be a neat 10 light years away. But 61 Cygni is by no means the absolute closest star to Earth, nor is it the strangest, not by a very long shot. Consider, for example, the famous star Betelgeuse, which ranks as the 10th brightest star visible in our night sky. Despite its extreme physical distance of roughly 450 light-years away from us, Betelgeuse is both staggeringly massive and unimaginably gigantic. It weighs at least 15 times the total mass of our Sun, and its physical diameter is almost completely unparalleled, stretching over 750 times the width of our local star. If this colossal red supergiant were to be placed directly into the centre of our own solar system, its bloated body would completely engulf Mercury, Venus, Earth, Mars, and the vast majority of the asteroid belt. Indeed, Betelgeuse is so incredibly bloated and distorted that it no longer maintains the clean shape of a perfect sphere. Advanced astronomical imaging exposes a highly lumpy, engorged stellar surface that boils violently with continuous convective turmoil happening underneath it. In the late months of 2019, the star unexpectedly began to dim dramatically, dropping from its comfortable spot as one of the top 10 brightest stars in the sky to ranking below 20th place. The true physical cause of this sudden, mysterious dimming was highly likely a massive plume of superheated plasma that the turbulent star had violently ejected out into space. As the plume travelled outward, it cooled down temporarily, forming a dense orbiting dust cloud that physically obscured the star's brightness from our perspective. Once the stellar debris finally cleared away, Betelgeuse rapidly returned to its former cosmic glory. However, Betelgeuse will not manage to last much longer on the cosmic timeline. It will soon terminate its life, likely sometime within the next 100,000 years, by exploding in a cataclysmic core collapse supernova. Theoretical calculations suggest that at its absolute peak brightness, the explosion will shine as brightly as a half moon in our night sky, making it instantly brighter than every other star and planet in existence. It will appear as a fierce, intense point of light that is almost uncomfortable to look at directly, producing more than enough ambient light in the middle of the night to comfortably read a printed book by. Yet, within a mere matter of weeks, the explosion will fade into total irrelevance, becoming entirely invisible to the naked human eye, leaving the constellation Orion to stand in the night sky, forever missing his right shoulder. But the vast, overwhelming majority of stars in our universe are not giants or supergiants. They are either mid-sized stable stars like our own Sun, or significantly smaller red dwarfs. This demographic reality includes Proxima Centauri, the absolute closest star to our solar system, a tiny red dwarf that can only be viewed through a powerful telescope due to its faintness. The star itself is structurally rather unremarkable, except for one monumental characteristic: it carries a planet along with it. That orbiting planet is a small, rocky world that possesses roughly the same physical size and mass as the Earth, and it orbits directly within the star's calculated habitable zone. Thanks to an intense observational campaign, officially known as the Pale Red Dot Initiative, a brilliant homage to the evocative pale blue dot photograph of Earth captured when Voyager 1 was at the far edge of the solar system, we now know that Proxima b, as the planet is officially named, represents humanity's closest chance to find a biological home outside our solar system. As of yet, of course, there is absolutely no firm guarantee that it can support life, as our modern observatories are simply not yet powerful enough to confirm the actual existence of living organisms there, let alone verify its vital prerequisites such as liquid surface water or a stable, protective atmosphere. To maintain long-term planetary habitability, planets orbiting red dwarfs must hug incredibly close to their parent stars. In the specific case of Proxima b, that world completes its orbit within just 0.05 astronomical units of its star, positioning it significantly closer to its parent Sun than Mercury clings to our own. This tight orbit is mandatory because the light and thermal energy radiating from red dwarf stars is incredibly feeble. It is only at that extreme close distance that a planet can absorb enough raw warmth to cling to the edge of habitability. However, if biological life did manage to find a home there, it would not experience an easy existence. Red dwarf stars are notoriously temperamental and volatile, highly prone to developing massive star spots that can completely cover half of their physical surface area at a single time, alongside sudden bouts of rage that flood their local planetary environments with violent electromagnetic storms of plasma. Consequently, their planets would alternate continuously between periods of extreme, freezing cold and sudden bursts of highly intense, lethal radiation. On top of this severe hazard, in all geographic likelihood, Proxima b is completely tidally locked, meaning one physical face of the planet is permanently pointed directly toward its star. This reality means that the companion sun never sets, nor ever rises on the planet's surface. Half of the world is permanently locked in never-ending frozen night, while the other half is roasted in continuous daylight. Yet, even this highly unusual environmental case does not automatically designate it as a completely dead world. Advanced computer climate modelling has shown that even these bizarre planets can successfully sustain life. The critical requirement is for the planet to possess a sufficient volume of water and a thick enough atmosphere to dynamically circulate heat around the entire planet, ensuring that the day side does not completely roast in the glare of the star, while the night side's air does not freeze solid and catastrophically collapse. The most fragile but deeply intriguing scenario is the concept of the so-called ribbon world, a descriptive term initially coined by the legendary science fiction author Arthur C. Clarke. Ribbon worlds are strictly habitable only within the narrow terminator regions of the planet, the thin, perpetual twilight zone slung between the two hemispheres, while the exact centre of the day side exists as a scorching, dry desert, and the night side remains a completely frozen wasteland. If atmospheric conditions are just right, a perfect thermal balance can emerge between the two extremes. This opens up a very thin strip of land girdling the entire planet, where temperatures remain completely stable, heated continuously from one side and cooled from the other. Proxima b is merely the absolute beginning of our interstellar catalogue. There exists a virtually endless variety of unique worlds scattered across the galaxy. At the absolute lowest scientific estimation, there is roughly one planet in existence for every single star, meaning that within the Milky Way galaxy alone, there are at least a few 100 billion planets. On the upper end of these statistical models, there could easily be trillions of independent worlds inhabiting our home galaxy alone. There are surely near-exact duplicates of our own solar system out there, featuring 4 rocky inner worlds and 4 outer gas giants. There are also significantly more unusual planetary arrangements, like the famous TRAPPIST-1 system, which consists of 7 rocky Earth-sized planets, all packed into incredibly close orbits around their small parent star, 3 of which reside securely within the habitable zone. There are massive gas giant planets orbiting so close to their stars that their outer atmospheres are actively being boiled away and destroyed. There are massive super-Earths and gas-shrouded mini-Neptunes. There are planets completely covered in thick hydrogen hazes that surround global surfaces entirely smothered in deep water, the fascinating Haitian worlds. There are planets so intensely hot that their rocks are actively glowing with thermal radiation, and worlds encased entirely in thick global sheets of ice. And there are even the mysterious rogue planets, worlds that possess no parent star or home system to call their own, flung out to wander completely alone through the endless black void. Of course, there was absolutely no physical way that the independent probe Batuta could ever hope to systematically catalogue every single one of them. Consequently, following its brief 10,000-year detour to investigate the unusual Algol system, it stuck strictly to its pre-planned trajectory, visiting a strategic string of star systems. As the autonomous spacecraft slowly made its way through the local Orion arm and began travelling inwards toward the dense galactic core, it fully understood that for the first million years of its journey, there would be nothing completely revolutionary to learn. There were no active signs of intelligent life or exotic breakdowns of fundamental physics to be located within this standard sector. To discover those, it would have to reach significantly further, travelling toward the violent core of the Milky Way itself and into the unknown beyond. The second major objective of the mission parameters was to locate a viable path to escape the gravitational hold of the Milky Way galaxy entirely. A sharp internal electronic alarm suddenly alerted Batuta. At that precise moment, it had just crossed the threshold of exactly 1 million years since its initial awakening as a conscious, independent entity, marking its literal millionth birthday. Currently situated midway through the expansive Scutum Centaurus spiral arm, the spacecraft was positioned roughly 15,000 light-years away from the core of the Milky Way. It had carefully nestled itself near an active protoplanetary disk, a massive, rotating ring of dense dust and gas material that was in the very beginning stages of planetary formation. Batuta had intentionally stopped its high-speed cruise here several thousand years ago to carefully prepare its systems for the next demanding stage of its long journey. It had originally intended to proceed onwards through the arm as quickly as possible, but the fascinating natural process of planet formation was simply too spectacular to ignore. Even with the vast eons of recorded human history preserved inside its database before it began its journey, human civilization had simply not existed long enough to watch this incredibly slow cosmic process unfold in real time. Consequently, Batuta made the independent decision to wait and watch. It would prove to be entirely worth the wait. The chronological history of planetary assembly is fundamentally the history of living things. This grand narrative initiates with the raw elemental building blocks that make biology possible in the first place. These elements are hydrogen, carbon, oxygen, nitrogen, and phosphorus. Devoid of this essential cosmic quintet, living organisms, as we currently understand them, would simply be an utter impossibility. The hydrogen component, of course, is the absolute easiest to trace back. It was manufactured directly within the roaring fires of the Big Bang at the absolute birth of the universe. This was a highly unique nucleosynthetic epoch that, for a few incredibly precious minutes, successfully transformed a dense plasma soup of fundamental quarks and gluons into a fixed population of basic hydrogen, helium, and a tiny smattering of lithium and beryllium. However, as the young universe rapidly expanded and cooled down from that initial cosmic inferno, these specific nuclear reactions ground to a halt, freezing the overall ratio of lightweight elements firmly in place. Early researchers successfully figured out this mechanism during the initial development phases of Big Bang cosmology. Yet a massive scientific question still lingered over the community. What about all the remaining chemical elements? And how exactly did complex items like carbon, iron, and everything else come to exist? To uncover the answer to this mystery, we must step back to the decade of the 1950s and look closely at a legendary scientific publication that has completely stood the test of time. Scientists almost never achieve major breakthroughs completely by themselves. Even a publication that features only a single listed author will typically display several individual names written out in the acknowledgement section at the very end, a clear indication that the principal writer received plenty of intellectual assistance along the way. While certain modern research collaborations managing massive particle experiments or planetary telescopes can easily stretch into hundreds of members, the majority of historical working groups were significantly smaller. They consisted of just a small handful of passionate individuals joining forces on a shared problem to discover something entirely brand new. Consequently, in the year 1957 at Cambridge University, a quartet of brilliant researchers gathered together who would permanently alter how human beings comprehend the wider universe. This historic document became widely celebrated across astronomy as the B²FH paper, named directly after the initials of its authors. The B² component represented Margaret and Geoffrey Burbidge, an iconic husband and wife astronomy duo. Margaret would subsequently go on to identify the most physically distant object ever witnessed by humanity in the year 1974, which was a highly faraway quasar, and she would also successfully verify that the massive galaxy M87 hosted a supermassive black hole directly at its centre. She achieved all of these monumental discoveries while continuously fighting against intense gender discrimination inside the field of astronomy. In fact, the couple once strategically switched their corporate job applications when Margaret was flatly turned down for a research role at the Mount Wilson Observatory, a rejection based entirely on the claim that the facility possessed only a single available toilet on site. Another iconic female astronomer named Vera Rubin would later relate this incredible story. She noted that with their typical brilliant adaptability, Jeff, who worked as a theorist, accepted the official Mount Wilson Fellowship while Margaret took the Kellogg appointment. Not surprisingly, whenever Jeff travelled out to Mount Wilson to conduct actual observations, Margaret coincidentally appeared right alongside him. The F initial in the paper's title stood for the legendary train enthusiast William Fowler. Fowler's extensive research into nuclear physics would eventually earn him the prestigious 1983 Nobel Prize in Physics. Yet, he once publicly stated that his absolute greatest personal treasure was a special gift presented to him by his devoted students and research collaborators for his 60th birthday. A fully functional scaled model of a British tank engine locomotive. Finally, the H initial stood for the infamously outspoken and controversial physicist Fred Hoyle, who 8 years prior had actually coined the literal term Big Bang Theory, and who would eventually be knighted by the Crown for his monumental contributions to modern astronomy. Their historic collaboration in 1957 effectively demonstrated to the world that it was active stars that were entirely responsible not only for the brilliant light that illuminates the dark universe, but for the systematic forging of all its heavy chemical elements. Absolutely all stars survive and maintain their structure by steadily burning hydrogen fuel deep inside their cores, leaving behind a dense nuclear ash composed entirely of helium. Toward the absolute final chapters of their stellar lifespans, stars resort to actively burning this accumulated ash, fusing helium atoms directly into carbon and oxygen. For smaller, lower mass stars like our own Sun, this specific phase marks the absolute end of their nuclear road, which ignites during their final deaths as supernova explosions. It is these cataclysmic supernova explosions that function as the ultimate cosmic factories, generating the immense levels of raw energy required to manufacture even heavier elements, thereby completely filling out the remaining slots of the periodic table. Since the initial publication of that landmark paper, the overarching scientific narrative of cosmic nucleosynthesis has been modified and updated as technology advanced. For example, in the year 2017, astronomers obtained their very first multi-messenger view of a spectacular kilonova, the high-energy collision and merger of two ultra-dense neutron stars. Over the course of only a few precious minutes, a global network of alert astronomers scattered across the world simultaneously witnessed the exact same event through both gravitational waves and electromagnetic waves across the entire light spectrum. Thanks to that groundbreaking observation, science now understands that colonovae also actively contribute a massive percentage to the heavy elemental population of the cosmos. Yet, despite these modern updates, the core scientific framework initially related by Woody Fowler, Fred Hoyle and the Burbages remains largely identical today. Following the violent death of every generation of stars, the surrounding cosmos becomes significantly enriched with fresh chemical elements, which join the swirling interstellar mixture, entirely prepared to participate in the next subsequent round of planet formation. Tens of thousands of these unique gas nebulae dot the landscape of the Milky Way galaxy, beautifully decorating its sweeping spiral arms like bright ornaments strung carefully across a holiday tree. No two individual nebulae are exactly identical to one another, which has caused astronomers to adopt the creative habit of naming them after whatever earthly shapes they happen to resemble, much like a person might spot an animal silhouette inside a cloud drifting by on a lazy afternoon. Perhaps the absolute most instantly recognizable of these structures is the famous Horsehead Nebula, located directly near the easternmost star of Orion's belt. It exists as a small, specialized subregion of a significantly larger gas complex, but it stands out in stark visual relief because its dense composition makes it appear pitch black against a vibrant, glowing background, measuring a little over 3 light-years across. The Horsehead Nebula functions as a highly active cradle of star formation. Its dense black clouds serve as a protective cocoon where newborn stars will soon physically emerge. Alternatively, consider the object designated NGC 6537, more commonly referred to by astronomers as the Red Spider Nebula, which sits several thousand light-years away from Earth. This complex arrangement of gas and dust does not represent the active birthplace of a star, but is instead a violent stellar funeral pyre. The outer layers of this dying star have been scattered violently outwards into 2 entirely opposite structural directions, with each expanding pocket forming thin, jagged spikes in space. Planetary systems always initiate their physical lives as highly diffuse, scattered clouds of basic hydrogen, helium, and a tiny sprinkling of heavier recycled elements. These clouds, formerly classified as giant molecular clouds, dot the interior of every single galaxy. In the early years of the 1900s, a prominent British physicist named Sir James Jeans discovered the exact physical process that allows these loose clouds to systematically turn into solid stars. Jeans calculated that if the internal hydrostatic balance of a stable molecular cloud is altered by an external force, it can trigger a process of rapid, runaway gravitational collapse. This delicate balance can easily be disturbed by a variety of cosmic events. However, under normal circumstances, active star formation is initiated inside a cloud whenever it physically passes directly through one of the massive spiral arms of a galaxy, while the spiral arms appear to completely dominate the architecture of galaxies. They are actually not that much denser than the dark gaps separating them, containing roughly only 10% more physical material. The diverse components of a galaxy, including these massive molecular clouds, orbit around the galactic centre at entirely different speeds, meaning they constantly pass in and out of the spiral arms over time. But whenever they pass directly through these compressed zones, a brand new round of intense star formation is ignited. This new generation of stars is visually dominated in sheer brightness by exceptionally massive, short-lived stars. These giant stars burn through their fuel and die off completely before the overall stellar cluster can finish making its way through the spiral arm, which causes the arms to appear significantly brighter than the rest of the disk, thereby giving a spiral galaxy its visible, recognizable form. Once a massive molecular cloud is set into motion, it becomes internally destabilized and begins to collapse rapidly under the weight of its own immense gravitational pull, triggering a self-reinforcing feedback cycle. The vast majority of the collapsing gas coalesces directly toward the absolute centre of the cloud, where intense friction heats the compressed gas to extreme temperatures, transforming it into a protostar. The remaining material that surrounds this central core spins faster and faster, eventually flattening out into a distinct disk plane around the protostar, marking the absolute beginnings of a protoplanetary disk. While much of this rotating disk is composed almost entirely of raw hydrogen and helium gas, sprinkled throughout the swirling chaotic system is a vital component of solid dust. Much like the tiny dust particles that naturally cling to the flat surfaces inside your own home, the microscopic dust grains inside a protoplanetary disk naturally stick together upon colliding. Meanwhile, as this slow process of planetary construction is underway, the infant protostar sitting in the centre begins to undergo a major physical transformation. Initially, it is heated strictly from the outside inward as incoming gas falls from the disk and violently slams into its core. But toward the absolute final stages of the protostar phase, just on the cusp of transitioning into a fully fledged star in its own right, it begins to generate heat directly from the inside outward, releasing massive amounts of energy and radiation in the form of intense stellar light. Finally, following all of these intense structural convulsions and systemic chaos, the core temperatures reach a critical threshold that ignites nuclear fusion, allowing the newborn star to settle into a hopefully long and stable existence. Within the hot inner regions of the disk, located closest to the young star, only the heaviest chemical elements possessing high melting points, such as iron, carbon, and silicon, along with their various molecular combinations, can successfully survive the intense radiation. Consequently, the inner regions of a solar system naturally become the exclusive home of small terrestrial rocky worlds. But far beyond this specific chemical demarcation line, the glare and thermal energy radiating from the young star are sufficiently feeble over the immense distances to allow volatile ices of water, ammonia, and nitrogen to remain completely solid. These solid ices mix intimately with the local dust and dirt, rapidly assembling massive planetesimals that grow significantly larger than their rocky inner siblings. This drastically increased physical mass generates a powerful gravitational field that quickly sucks in massive envelopes of surrounding hydrogen and helium gas from the disk. The very first planetesimal to successfully complete this phase wins the ultimate gravitational prize, transforming into the largest planet of the system, thanks to its independent ability to completely monopolize the remaining gas supply of the disk. Consequently, the subsequent gas giants that try to assemble afterward are forced to fight desperately amongst themselves over whatever scrap gas is left behind. These highly intense, chaotic gravitational battles ultimately end up violently ejecting many planetesimals, and even some fully formed planets completely out of the star system altogether. In our own local solar system, the massive giant planets initially formed significantly closer to the Sun than they reside today, assembling in regions where there was more than enough raw material to create their massive sizes. But as the surrounding gas disk cleared out over time, the mutual gravitational attraction between the planets dynamically pushed them outwards to their contemporary planetary positions. In fact, advanced dynamic models suggest there may even have been a fifth large gas planet initially created alongside them that was violently ejected into interstellar space during this chaotic migration process. Planetary bodies can even form completely independently of any parent star. The fascinating exoplanet designated WISE 0855-0714, initially discovered by human astronomers in the year 2014, stands as a prime example of this phenomenon. It is truly gigantic, measuring roughly 10 times the total mass of Jupiter, yet it sits only 7.2 light-years away from Earth, positioning it significantly closer to us than the vast majority of normal stars visible in our night sky. Sitting in the cosmic classification zone between these free-roaming rogue planets and genuine active stars are the enigmatic brown dwarfs, which were first identified by a dedicated team of Caltech and Johns Hopkins astronomers in the year 1994. Brown dwarfs are massive enough to briefly sustain the nuclear fusion of deuterium deep inside their cores, but they simply do not possess the required mass to ignite true hydrogen reactions and reach the stable main sequence. Instead, they simply exist and slowly cool down over time. To quote a memorable remark from Geneva Shulksani from the original Caltech discovery team that located the very first one, "It looks exactly like Jupiter, but that is precisely what you would expect for a brown dwarf." These fascinating formation processes repeat generation after generation, star after star, across nearly countless billions of systems, systematically filling each and every galaxy with a massive population of unique planets. It was an absolute delight for the independent explorer Batuta to patiently watch this minor natural miracle unfold in real time. But no matter how deeply it was entranced by this planetary birth, it could not afford to stay there forever. Batuta had to resume its primary journey. This time, it moved forward with absolute purpose. It set its navigation sensors directly on the dense centre of the Milky Way galaxy, plotting a path through the innermost spiral arms and into the dense core itself, with the sole ultimate purpose of coming face to face with the system's supermassive black hole and exploring the distant darkness that lay beyond. Following a grueling interstellar journey that spanned nearly 10 million years, Batuta had finally successfully reached the absolute outskirts of the core of the Milky Way. The galaxy's central core is structurally shaped like an elongated bar, and the independent spacecraft had found itself positioned just past the inner spiral arm. Though getting to this deep sector was by no means an easy navigational task, Batuta strongly suspected that it was not the first advanced craft to make it to these profound depths. Somewhere within the distant Norma spiral arm, situated some 5,000 light-years rimward of its position, the spacecraft's long antenna suddenly detected an incredibly faint staccato radio signal. At first, the probe's computer suspected it was merely tracking just another ordinary pulsar, but the specific spectral signature of this radio emission did not match any known stellar database. Instead, upon conducting a significantly deeper automated inspection, the staggered rhythm of the broadcast was all too familiar to the machine. It was entirely artificial in origin, the exact kind of structured signal that Batuta would have manufactured itself. Consequently, to leave its own permanent mark on the sector, Batuta designed its own highly unique planetary calling card. It spent the next 10,000 years carefully and systematically manipulating a dead, stable star system, intentionally guiding all of its local rocky planets to catastrophically crash directly into their parent star. This deliberate cosmic demolition project dramatically raised the atmospheric abundance of heavy chemical elements inside the star, pushing it well above what any ordinary star of its specific natural type should ever possess. Within about 20,000 years, the human race, alongside any other advanced technological spacecraft travelling through this specific corner of the galaxy, would inevitably notice a sudden and highly bizarre spike in heavy metals polluting this star. Perhaps those future researchers would ascribe the anomaly to some completely natural planetary phenomenon, or perhaps they would correctly assume it was the deliberate machinations of one of their long-lost, wayward exploratory probes. Or perhaps they would not even manage to notice it at all, assuming they were even still alive to look. And so, with its grand journey so far spanning a total timeline of 10 million years, Batuta had finally started to feel old. But still, after absolutely everything it had independently witnessed and experienced across the vacuum, it could not hold a candle to the most ancient living denizens of the galaxy, some of whom Batuta had the immense honour of directly encountering. One of those ancient enduring stars is known simply to modern astronomers as the Methuselah star. This incredibly old star was named after the famous biblical figure who was reported to have lived for a staggering 969 years. More formally, the star carries the official scientific label of HD 140283, but it suddenly shot to global fame across the astronomical community when researchers calculated an entirely unexpected age for it. According to some early calculation models, the star was estimated to be older than the entire universe itself, coming in at an age of over 14 billion years. This baseline calculation caused many scientists to wonder if the existence of the Methuselah star completely threatened our fundamental understanding of Big Bang cosmology. Other intellectuals pondered whether it called into question our most foundational comprehension of basic stellar physics, but no matter what the final answer would be, the Methuselah star was undoubtedly ancient, and it possessed an immense amount of knowledge to teach us about the early cosmos. Calculating the precise age of an individual, isolated star is an incredibly tricky scientific task. For centuries, astronomers had absolutely no clear idea how to do it, observing only that a spectacular variety of unique stars inhabited the galaxy. There were mid-sized yellow-white stars like our own Sun, tiny red dwarfs like our absolute closest neighbour Proxima Centauri, and massive giants that existed in both blue and red varieties like Rigel and Betelgeuse respectively. In the final years of the 1800s, astronomers began to believe that all stars started out their lives exceptionally large and hot, and then slowly shrank and cooled down over the course of their lifespans, emitting light during the process. But a few decades later, a brilliant scientist named Sir Arthur Eddington calculated that if this specific life cycle theory was correct, then our own Sun could only possess a maximum lifetime of a few million years. This small number was embarrassingly out of step with the billions of years clearly implied by the fields of terrestrial geology and biological evolution. Eventually, the true structural keys to unlocking stellar evolution emerged from the steady, meticulous eye of Annie Jump Cannon. She was one of the famous women computers hired at the Harvard Observatory and tasked with the exhausting, repetitive daily chore of sifting through massive quantities of photographic stellar data. Hired at a rate of roughly 25 cents per hour, these women computers were initially chosen by administration simply because they were significantly cheaper to employ than the $1 per hour it would have cost to hire men. Yet, they would go on to accurately analyse and catalogue the true brightness and celestial positions of thousands of stars. Cannon herself would later state that no scientific discovery is ever too small to matter, for even the absolute tiniest piece of fresh knowledge can eventually lead to monumental advancements in our collective understanding of the world. Her remarkable professional achievements served as a shining example of this philosophy, as she independently proposed the modern stellar classification scheme that would ultimately unlock the mystery of how stars live and die. To initiate the project, the computers had initially developed a basic alphabetical ordering scheme, but as time moved forward and more data was analysed, that system was simplified and completely reordered, leaving us with the famous sequence O, B, A, F, G, K or M, An O-type star represents the absolute hottest category of star in existence, while an M-type star represents the coolest. Building directly upon the groundbreaking work of these Harvard computers, two independent astronomers named Einar Hertzsprung and Henry Norris Russell devised a highly clever type of data plot that directly compared the total luminosity of a star population against their temperature. By analysing this distribution, they discovered that the vast, overwhelming majority of stars sat neatly along a continuous diagonal track that showed a tight, locked relationship between these two physical properties. Today, modern science calls this specific chart a Hertzsprung-Russell diagram, and we refer to that prominent diagonal track as the main sequence. As stars grow older over time, they slowly move along this main sequence line, meaning the chart tells astronomers roughly where a star currently sits in its overall life cycle. Under normal parameters, stars start their lives slightly dimmer and redder, and they tend to grow increasingly bright and bluer as they age. It is the absolute initial mass of the star that dictates exactly where it will start its journey on this track, and exactly how many millions or billions of years it will manage to stay on it. If astronomers possess direct access to an entire cluster of stars born at the same time, they can carefully calibrate the interlocking relationships between physical size, colour, temperature, and the specific quantity of heavy chemical elements to derive an exceptionally accurate gauge of the cluster's overall age. However, this helpful calibration technique only functions well when analysing an entire connected population of stars. Determining the precise age of a single isolated star remains an entirely different story that is extremely challenging, and the Methuselah star was certainly no exception to this rule. The eventual solution to the complex riddle of the Methuselah star, much like the vast majority of solutions to deep riddles within modern astronomy, came down to the mathematics of scientific uncertainty. There is absolutely no doubt that this star is ancient, existing as one of the oldest stars to ever live inside the Milky Way galaxy, but it certainly formed well after the Big Bang occurred. It is simply a matter of the mathematical uncertainties associated with calculating its age being so incredibly large that, on paper, it can accidentally appear to be older than the universe itself. Despite its extreme age, Methuselah is still not the absolute oldest possible category of star to still inhabit the modern Milky Way. That is because Methuselah belongs to a specific generation of stars known to science as population 2 stars. To fully comprehend what that classification means, we must step back more than 80 years to the year 1942 and look at an apparent military attack happening directly on American soil. The nighttime skies over the city of Los Angeles are completely on fire, air raid sirens are loudly wailing, anti-aircraft artillery guns are firing continuously into the dark, and a total emergency blackout is being ordered across the entire city. A staggering 1,400 artillery shells would be fired into the sky that night as the entire civilian population is thrown into complete chaos. Yet, at the end of the night, there would be only 5 casualties reported, 2 individuals dying from sudden heart attacks, and 3 people killed in car accidents caused by the distraction of the exploding artillery shells. The entire incident would later turn out to be a total false alarm, triggered initially by a loose floating meteorological weather balloon. The intense civilian anxiety built up by the devastating surprise attack on Pearl Harbor 2 years prior had gone off like a literal powder keg. These strict military blackout restrictions would remain firmly in place for the next 18 months to protect the coast from potential attacks by enemy submarines. However, for a highly clever German astronomer living in Los Angeles named Walter Baade, these dark blackouts presented a truly remarkable scientific opportunity. Using the famous 100-inch Hooker telescope situated at the Mount Wilson Observatory, the exact same instrument through which Edwin Hubble had discovered an expanding universe just 15 years before. Barda seized directly upon the drastically reduced city light pollution to clearly resolve individual stars around the centre of the neighbouring Andromeda galaxy. He successfully utilised these unique observations to define two entirely distinct stellar populations, Population 1 and Population 2. Population 2 stars are ancient stars that possess only a medium, conservative amount of heavy chemical elements polluting their outer atmospheres. Meanwhile, stars like our own Sun are categorised as Population 1 stars, which feature a significantly higher concentration of metals. Metals is the generic, loose term that astronomers use to categorise absolutely every single chemical element on the periodic table that is heavier than hydrogen and helium. Though to be completely fair, basic hydrogen and helium make up more than 98% of all the matter in the entire universe. So it is not entirely unfair for chemists to consider the remaining elements of the periodic table a mere rounding error. These Population 1 and Population 2 stars, including the ancient Methuselah star, are the direct structural inheritors of multiple previous generations of stars in our universe. With the conclusion of each generation, the cosmos becomes increasingly enriched compared to the previous era. Following every stellar death, more heavy elements forged in the core of a star, or during a supernova explosion, circulate into the interstellar medium, meaning each subsequent round of stars possesses a higher fraction of those heavier elements. But the very first stars to ever appear in our universe possessed absolutely no heavy elements to speak of. They were as pure as they could possibly be, composed entirely of primordial material. This initial generation of stars is formally known to science as Population 3 stars. This seemingly reversed naming system is simply the result of their existence being proposed by theorists years after Population 1 and Population 2 had already been established. A delay caused by the fact that not a single Population 3 star has ever been found by modern telescopes. Science is still not entirely certain exactly how the very first stars formed, but models suggest they were likely absolutely huge. This massive size is predicted because modern-day stars require the presence of heavier metallic elements to help moderate and slow down their internal nuclear fusion chain reactions. These metals also actively help collapsing protostellar gas clouds efficiently release their heat radiation, allowing them to fragment into smaller segments before igniting fusion. But the first stars possessed neither of these chemical advantages. Consequently, they had to form without any metals at all, meaning their primordial gas clouds could remain at enormous spatial scales without breaking apart into smaller pieces. In fact, some advanced models of initial stellar formation suggest that individual Population 3 stars may have been over 100 times more massive than our Sun, while other, more exotic mechanisms suggest they could have reached a staggering 1,000 or even 10,000 solar masses each. Either way, at that titanic mass scale, they were doomed to lead incredibly short, intense lives, for with greater structural mass comes a drastically increased rate of core fusion reactions. At 100 solar masses or more, the first Population 3 stars would have lived incredibly fast and died exceptionally young, surviving for only a few million years total. Since these stars initially arose during the dark ages of the cosmos over 13 billion years ago, this entire initial generation came and went well before the development of the very first galaxies. The only possible chance a Population 3 star had to survive into the modern era is if it managed to enter the main sequence as a relatively tiny object, smaller than our Sun, and remain completely hidden and protected from absorbing heavy elements over the eons. But the statistical chances of finding such a rare object are so incredibly slim that modern-day astronomy has turned to massive space-based instruments like the James Webb Space Telescope to instead hunt for their faint ancient light signatures at the extreme edge of the universe. This is light that was originally sent out when the cosmos was first forming its very first stars and structural galaxies. Generations of stars come, and generations of stars go, a continuous sequence stretching back billions of years. While all stars share the exact same fundamental process of initial formation and share the same main sequence phase of hydrogen burning inside their cores, different categories of stars encounter completely different final days. To begin with, the absolute smallest stars in the universe, the tiny red dwarfs, simply and quietly fade away into the dark night. They require only a relatively tiny amount of core fusion reactions to physically maintain their structure against gravity. Because of this slow fuel consumption, they glow only very dimly, functioning at a level almost 1,000,000 times less luminous than our Sun. But because they burn their fuel so slowly, they live enormously long lives, with lifespans extending up to trillions of years before they will finally run out of hydrogen. Mid-sized stars like our Sun, however, face a much more dramatic and chaotic fate. When they first exit the stable main sequence, they undergo a rapid series of intense structural changes that see them swelling outward to become enormous red giant stars, then collapsing inward again, then reigniting their shells back and forth. But at the absolute end of it all, following billions of years of calm main sequence life, violent transitions to helium burning and chaotic muscular spasms, all that remains of a mid-sized star is a white dwarf. This object is the leftover naked core of carbon and oxygen. But when white dwarfs were initially discovered by astronomers in the year 1916, many intellectuals thought they were downright physically impossible, assuming the observers had made a terrible mistake. Sir Arthur Eddington perfectly summarised this scientific confusion when he pondered a hypothetical dialogue between modern astronomers and the universe. The cosmos has offered astronomers a bizarre scenario where a full ton of a star's physical material could easily squeeze inside a small matchbox. The collective scientific community reacts to this wild concept with a simple, blunt reply: be quiet and stop talking total nonsense. But Ernst Öpik, a brilliant Estonian astronomer who conducted some of the very first concrete observations of these white dwarfs, stood firmly by his data, maintaining that his calculations clearly proved some of the stars he analysed possessed material densities over 25,000 times greater than that of our Sun. Today, we know with absolute certainty that he was right, and white dwarfs would become just the first of many ultra-dense structural surprises that the universe had waiting for us. Because of this, astronomers quickly learned never to tell the cosmos to be quiet. Despite their incredible physical mass, white dwarfs occupy an exceptionally small spatial volume, measuring roughly the size of a terrestrial rocky planet like Earth. Because they are the literal leftover cores of what was once a roaring nuclear furnace inside a living star, when they first emerge from their dusty stellar cocoons, they possess extreme surface temperatures reaching upwards of 10 million Kelvin. At these unimaginable temperatures, they emit massive amounts of lethal X-ray radiation, entirely flooding their surrounding planetary systems with deadly high-energy light. But these dying systems are also filled with the expansive, leftover atmospheres that the stars heaved off. What follows next is a physical process highly similar to the mechanism found inside everyday fluorescent light bulbs. The energetic X-rays deliver raw energy to the surrounding gas clouds. A portion of this energy goes directly to increasing the internal energy level of the gas electrons. Those excited electrons eventually fall back down into lower energy states, and during that transition they release radiation of their own, but this time at wavelengths that are significantly less lethal and vastly more beautiful to look at. These glowing clouds are the famous planetary nebulae, a term initially coined by William Herschel in the late years of the 1700s. He was completely mystified by their unusual appearance, which to his eyes closely resembled a faint fuzzy planet drifting in the dark. As is usually the case in the astronomy profession, by the time researchers finally realised these strange objects were actually the direct result of stellar deaths, the planetary title had already permanently stuck. No two individual planetary nebulae are exactly identical to one another, as their final geometry depends entirely on the highly complex, chaotic intertwining of different chemical elements as a dying star systematically heaves off its outer gas layers. A great many of them can be observed through basic telescopes, exposing a galaxy beautifully twinkling with unique cosmic ornaments of different shapes, dimensions, and vibrant colours. Adding significantly to their overall beauty is their exceptionally short-lived nature. As the central white dwarf cools down over time, after about 10,000 years it will completely stop emitting that intense X-ray radiation. Once that happens, the surrounding planetary nebula will permanently fade from the cosmic scene, never to be repeated again. If a white dwarf is left completely alone in the vacuum, it too will slowly and steadily cool down. But because they are so intensely hot and compressed into such a tight space, they are remarkably long-lived objects. White dwarfs require tens of billions of years to fully radiate away their heat and fade into total blackness. Because of this immense timeline, there are absolutely no completely cold white dwarfs, objects sometimes referred to by theorists as black dwarfs, existing anywhere in our modern universe. There simply has not been enough time since the Big Bang for one to form. While the majority of white dwarfs are typical of their class, a few unique specimens stand out. One example is Janus, a highly unusual white dwarf that features two completely distinct hemispheres, one side dominated by hydrogen gas, and the opposite side covered in helium. Another is the star designated WDJ 2147 for 2.35, which is exceptionally and remarkably cool. Possessing a calculated age of over 10 billion years, it stands as one of the absolute oldest white dwarfs known to science, maintaining a surface temperature of only a few thousand degrees. However, if a white dwarf happens to possess a companion star, it can experience a far more dramatic and explosive fate. As the companion star nears the final chapters of its own life course, it will swell outward to become a massive red giant. If that expansion is large enough, the outer material from the giant star will overflow and begin to pour directly onto the surface of the white dwarf. Because of the white dwarf's intense gravitational field, this accumulated hydrogen envelope reaches incredible material densities, eventually becoming hot enough to spontaneously trigger a runaway nuclear fusion reaction. In a sudden flash, all of that stolen hydrogen ignites at once, generating a colossal nuclear blast known to astronomers as a classical nova. Yet if enough hydrogen continues to accumulate on the surface before burning off completely, a true cosmic catastrophe can strike the system. This triggers a total, uncontrollable, runaway nuclear detonation event, with a small spark of extreme fusion racing across first the face and then the entire body of the star, completely ripping the white dwarf apart in a single tremendous explosion. This specific phenomenon is a particular category of supernova, a cataclysmic explosion capable of easily outshining the combined light generated by hundreds of billions of normal stars shining together. A relatively quiet galaxy like our Milky Way only manufactures a small handful of these specific supernovae every single century. Since the vast majority of these events occur exceptionally far away from Earth behind dense dust clouds, we should count ourselves incredibly lucky to ever see them at all. But there exist other categories of even more energetic supernovae, and their explanation starts with an exceptionally rare mystery in our skies. The year was 1867, and the Paris Observatory was proudly celebrating 200 years of systematically watching the heavens. Initially established back in 1667 during the historical reign of King Louis XIV, it stands as one of the truly great foundational observatories of modern astronomy, situated on a small hill on the southern edge of Paris. At the time of its initial construction, the facility was located far enough away from the daily hustle and bustle of the main city that its astronomers could enjoy a pristine, clear view of the night sky, while remaining close enough to maintain direct access to the cultural and scientific elites living inside the capital. King Louis XIV had even attempted a bold national claim for the Paris Observatory to officially mark the international point of the prime meridian, which also would have conveniently passed directly through his personal throne room inside the Louvre Palace. Consequently, it was at that exact facility, 2 centuries later with Napoleon III sitting on the throne, that 2 dedicated astronomers named Charles Wolf and Georges Rayet made the profound discovery that bears their names today. They successfully located 3 unusual stars that displayed spectral emission lines that were significantly broader than anything ever recorded before. A clear explanation for this bizarre atomic behaviour would remain completely elusive to science for many decades. One major reason for this long delay is that Wolf-Rayet stars would turn out to be extraordinarily rare objects. Even today, with the full suite of advanced modern technology available to global astronomy, only about 500 of these unique stars have ever been detected inside our galaxy. Consequently, it was not until nearly the turn of the 20th century that astronomers would finally uncover the real truth. These wide spectral features were due directly to the massive presence of helium, an element that had actually been discovered by science just a single year prior to Wolf and Rayet's initial observations, combined with a physical mechanism known as Doppler broadening. When a gas cloud becomes extremely hot, its individual spectral lines broaden significantly due to the erratic, high-speed kinetic motion of the hot gas molecules. This discovery implied that whatever was happening inside Wolf-Rayet stars involved an absolutely immense amount of raw energy. It ultimately turned out that Wolf-Rayet stars are so rare because they represent a very brief, temporary phase of stellar life. They are ultra-massive stars rapidly nearing their final operational days. As the outer atmospheres of these giant stars are violently blown away by successive red giant phases, they produce highly distended thick envelopes of expanding gas. The high-energy radiation coming from the core strikes this envelope, exciting the surrounding gas and causing it to glow brilliantly on its own, thus creating those strange spectral features. But what comes next on their timeline is the real danger, because Wolf-Rayet stars are widely recognised by theorists to be the direct precursors to a Type II supernova. Absolutely any star in the universe that is born larger than roughly 8 times the total mass of our Sun shares this grim, if spectacular, fate. Their fundamental structural flaw is that nuclear fusion, the powerful chemical reaction that can successfully power a star for eons, can never truly win in the long term against its ancient relentless foe, gravity. Gravity is relatively weak in comparison to the other fundamental forces of nature, but what it lacks in immediate strength, it more than compensates for with immense patience. Quiet, continuous, incessant patience. The crushing gravitational pull of a star's own massive weight is always attempting to collapse the object, trying to shrink its material into a smaller and smaller volume. Resisting that continuous inward pull is the outward thermal energy released from nuclear fusion. A star can successfully maintain that delicate balance for millions, billions, or even trillions of years, but there is only a finite supply of fuel available inside the core of a star. Once the initial hydrogen fuel runs out completely, the star must switch to fusing helium, which is not nearly as energetically efficient. Once the core helium runs out, a massive star can instead begin burning carbon and oxygen. Once that runs out, it can move on to even heavier elements. But at each progressive phase, the fusion process yields less and less outward energy. Because of this, the life cycles catastrophically shrink. Hydrogen can burn stably for millions of years, helium for less than 1 million, carbon for only a few hundred years, neon for half a year, oxygen for a matter of days, and silicon for only a handful of hours. Then comes iron. Under the crushing gravitational weight of the star pressing inward, iron begins to fuse to produce heavier elements. But here, a fatal physics problem emerges. Iron fusion does not release energy. Instead, it absorbs it. With absolutely no outward energy left to counteract gravity, the star instantly collapses inward. In only a few more seconds, the star will be completely dead. The internal pressures reach such mind-boggling extremes that the iron inside the core converts into something entirely strange and unique in the universe. The free electrons are violently forced directly inside of atomic nuclei, where they merge with protons to produce neutrons. The entire massive core instantly transforms into a sphere only a few kilometers across, composed of almost pure neutrons. The rest of the star's outer layers rush violently inwards toward that solid neutron core at a substantial fraction of the speed of light. When the infalling material strikes the core, it meets an unyielding wall of resistance and bounces violently back outwards, launching a powerful shockwave that ripples through the remaining stellar interior. But exactly what happens next in those moments remains a deep mystery to modern physics. This is true despite the fact that the actual existence of this category of supernova has been documented by the human race since before the dawn of recorded history. Indeed, the absolute earliest historical observations of a supernova consist of simple rock carvings created by unknown prehistoric peoples around the year 4000 BC. Some of these supernovae were so incredibly bright and persistent that entirely different cultures around the world simultaneously recorded the exact same event. In the year 1054, Chinese court astronomers recorded a prominent new guest star suddenly appearing in their skies. At the exact same time, half a world away, the ancestral Puebloan people of modern-day New Mexico created a detailed rock pictograph denoting this special celestial event. Today, that exact portion of the sky is occupied by the famous Crab Nebula, the beautiful, expanding remnants of that ancient, mighty explosion. But it was in the early 20th century that the brilliant astronomer Fritz Zwicky started to deliver real scientific answers. For millennia, human cultures had observed different kinds of new stars appearing in the dark. Now, thanks to the sophistication offered by modern astrophysics, he could systematically classify them. The temporary flashes of hydrogen envelopes around white dwarfs would retain the classic name of nova, which simply means new. Meanwhile, these massive explosions would be called supernova. When a white dwarf is completely destroyed, it is a type 1a supernova. When a massive star meets the end of its life, it is a type 2. In the year 1987, a brilliant blast originating inside the nearby Large Magellanic Cloud made history when it became the very first supernova to be detected, not by looking up into the sky, but by looking down into a giant tank of water. That specialised tank was the famous Kamiokande 2 detector, buried deep underground inside the Mozumi mine in Japan. It held over 1,000 metric tons of ultra-pure liquid water, surrounded by thousands of highly sensitive photodetectors. All of these synthetic eyes stared incessantly at the water within. Kamiokande 2 was designed specifically to detect neutrinos, the nearly massless particles that slip completely through the cracks of the cosmos. Neutrinos flood our universe. There are currently several trillion of them passing completely through your body right now, but they only extremely rarely interact with ordinary matter. Because of this, for most of human history, they went completely unnoticed. It requires enormous detector volumes to catch even a few. Nuclear reactions create neutrinos, and our Sun produces copious amounts of them every single day. When the supernova of 1987 detonated, it created roughly 10 to the power of 58 neutrinos. The vast majority missed Earth, but of those that hit Kamiokande 2, instruments detected a grand total of 25. But capturing those 25 individual particles was more than enough to validate the mathematical framework that had been developing in the minds of theoretical physicists to explain how these massive explosions actually complete their detonations. The major hurdle had been that early computer models showed the expanding shock front, manufactured when the collapsing stellar atmosphere slams into the solid neutron core, slows down and completely stalls out, failing to deliver anywhere near enough mechanical energy to tear the rest of the star apart. But neutrinos effectively step in to save the day. The rapid transition of raw iron into pure neutrons inside the core generates an absolute crushing flood of these subatomic particles. In fact, over 99% of the total energy released during a core collapse supernova is carried away in this neutrino production. The immense flash of light that human beings visually observe is a mere shadow in comparison to this invisible particle surge. Of course, the vast majority of these neutrinos slip effortlessly out of the dying star and vanish into the cosmos, never interacting with anything again. But a tiny fraction of them do manage to interact with the dense infalling stellar material, transferring enough energy to reignite the stalled shockwave, which allows it to successfully break through and blast the star apart. Other complex physical mechanics, such as out-of-control resonant fluid, instabilities similar to the dangerous forces that destroyed the Takama Narrows Bridge back in the year 1940, might also play an essential role in this process. Regardless of the precise subatomic mechanism, once that powerful shockwave successfully breaks out of the core, it sweeps up all the material in front of it like an unstoppable cosmic avalanche, taking the star's remaining atmosphere and accelerating it outwards at nearly the speed of light. Intense nuclear reactions occurring within this moving shock front finally create the heavy elements that the core had attempted to forge mere minutes prior. Long after the primary star is completely dead and gone, the expanding remnants of its atmosphere remain behind as a slowly growing and cooling nebula that eventually disperses its enriched ingredients into the interstellar medium. As for the independent AI explorer, Batuta, this particular supernova caught it completely unawares. Over the millions of years that had passed since its initial activation, the probe had grown somewhat complacent and overconfident in its own safety. It believed it had seen absolutely everything, understood all of nature's laws, and knew precisely when the universe was safe and when it was dangerous, or so its processing units assumed. The vehicle had been quietly refueling its energy reserves inside a long-dead binary star system when a sudden, blinding burst of neutrinos and lethal gamma rays arrived as the only advance warning before the neighbouring companion star split itself apart, sending a massive shockwave racing outwards. It required over 1,000 years of automated maintenance for Batuta to fully repair the extensive structural damage it sustained, slowly licking its wounds while drifting through the tattered, irradiated remnants of that ruined system. Grim and deeply determined, the machine decided that it had spent more than enough time exploring the standard sectors of the galaxy. With its previous arrogance completely blown away by the explosive companion of the White Dwarf, it recognised that it was time to encounter the supermassive black hole at the centre of our galaxy once and for all, and to leave the Milky Way behind forever. Eventually, Batuta hung balanced directly on the absolute edge of the ultimate abyss, Sagittarius. A star, the monster black hole residing at the very heart of the Milky Way galaxy, was positioned dead ahead of its sensors. The advanced spacecraft had deployed a massive array of specialized telescopes spanning across the entire electromagnetic spectrum. For this truly was a visual marvel to behold. All of the immense structural struggles it endured to reach this location, spanning nearly 10 million years of flight since it first exited the heliopause gates of our solar system, were more than worth the cost. The environment immediately surrounding this supermassive black hole was easily the most continuously energetic, violent location in the entire galaxy. Beneath all of that chaos, resting underneath the blinding maelstrom of glowing plasma spinning around it and the crushing flood of radiation emanating near its boundaries, lay the pitch-black heart itself, the event horizon that permanently cuts off the internal interior from the rest of the observable universe. For a brief operational moment, Batuta was intensely tempted to plunge itself directly beneath those dark depths out of pure, unadulterated scientific curiosity. Prior to its launch from Earth, the human race had not yet managed to crack the profound riddle of quantum gravity, the theoretical framework needed to provide a coherent, universal description of intense gravitational forces operating at subatomic scales. The ultimate answer to that mystery was resting right there, hidden inside the singularity at the centre of the beast. But the machine knew it was a total trap. If Batuta directed itself below that dark horizon, it would successfully learn nature's most closely held secret, but it would never be capable of returning home to deliver the answers to its creators. It was actually those exact same singularities, those mathematical riddles of infinite density existing at the centre of black holes, that initially caused the scientific community to doubt their physical reality altogether. In a groundbreaking 1915 letter sent directly to Albert Einstein from the dangerous front lines of World War I, a German physicist named Karl Schwarzschild wrote that the war was being surprisingly kind to him, allowing him, despite fierce gunfire happening at a decidedly terrestrial distance, to take long intellectual walks into Einstein's wonderful land of ideas. Schwarzschild had volunteered for military service at the age of 40, and while serving on the Russian front, he managed to calculate the very first exact mathematical solution to Einstein's newly published general theory of relativity. He successfully solved the complex equations for the specific case of the gravitational influence generated by a perfectly spherically symmetric object. Just 1 year after that breakthrough, a great mathematician named David Hilbert verified that Schwarzschild's unique solution completely broke down at the absolute dead centre of the calculated object. This mathematical failure meant that any attempt to describe the physics of gravity at that central point yielded completely nonsensical, infinite results. Something incredibly bizarre was happening inside those calculations, an entirely unexpected mathematical anomaly. The theoretical exploration of black holes had officially begun. Singularities occasionally appear in all sorts of different physical theories, but scientists can usually explain them away by looking at the practical limits of the materials involved. For instance, the calculated force of a mechanical spring approaches infinity as the spring is compressed tighter and tighter. This specific mathematical singularity is never a practical problem for engineers, because we know that real springs cannot physically be compressed forever. Eventually, another physical force, such as the electromagnetic repulsion between the individual molecules, prevents the material from getting any smaller. But the unique singularity that appeared inside Schwarzschild's relativity solution was fundamentally different. It flatly implied that if a concentration of matter became too heavy, a region of the universe would form where gravity became so overwhelmingly strong that something completely unknown to science would occur. The vast majority of astronomers initially scoffed at the idea. In fact, Albert Einstein himself is famously quoted as having published a paper stating that the essential result of his investigation was a clear, definitive understanding as to why these Schwarzschild singularities do not actually exist in physical reality, but a small, passionate minority of researchers, including Robert Oppenheimer, long before he became deeply involved in the operations of the Manhattan Project, carried the theoretical work forward. In the year 1972, astronomers finally came across Cygnus X1, which stood as one of the absolute brightest sources of high-energy X-rays in the entire night sky. The system was composed of two closely interacting objects, a massive, bright star and a smaller, completely unseen companion body. Initial orbital calculations suggested something incredibly enticing to the community. The derived mass and tiny physical radius of the invisible companion indicated that it was significantly denser than any other known astrophysical object in existence, dense enough to be a genuine black hole. Consequently, in the year 1975, Stephen Hawking and Kip Thorne, two legendary pioneers of black hole physics, decided to make a famous professional bet with one another. They had both spent the vast majority of their academic careers studying these hypothetical objects, completely staking their professional reputations on their real-world existence. If it turned out that black holes did not actually exist in nature, they would both effectively be out of a job. Therefore, they concocted the bet as a humorous consolation prize. If black holes were proven to be a total myth, then Thorne owed Hawking a full 4-year subscription to the British satirical magazine Private Eye. But if they were proven to be real, then Hawking owed Thorne a 1-year subscription to the slightly less satirical American magazine Penthouse. By the year 1988, Hawking officially admitted defeat and paid his dues to Thorne. And with the verified reality of black holes came the undeniable reality of gravitational singularities. The physical, spatial extent of a black hole's internal singularity is, as far as science currently understands it, through the mathematics of general relativity, exactly zero. Black holes occupy absolutely no physical volume in space. They possess no structural breadth, no height, and no depth whatsoever. They are literal defects, permanent punctures torn directly into the smooth fabric of spacetime itself. In a highly unique way, singularities are quite akin to subatomic particles like electrons or top quarks, which also possess no measurable spatial extent. Strictly speaking, there is no physical width to an individual electron. There are only localized ranges that define how it interacts with other surrounding particles. Yet, despite possessing no physical size, these objects can feature wildly different masses. Therefore, in one literal sense, absolutely all black holes in the universe share the exact same physical size, which is no size at all. But they do possess varying amounts of mass. They are composed entirely of all the original stellar material that initially collapsed to create them, combined with all the subsequent matter that has suffered the unfortunate fate of falling too close to their borders. black holes can and will actively eat absolutely anything that crosses their path. Any source of matter or energy functions as viable food for them. Incoming radiation, dark matter, subatomic particles, giant molecular clouds, and even entire intact stars or other black holes. Absolutely anything that encroaches within the boundary of the event horizon can never return to the outside universe, doomed to always end up at the central singularity. While black holes do not possess any stronger gravitational pull than a normal object of identical mass, meaning that if you were to replace our Sun with a black hole of equivalent weight, the planets would remain safely in their exact same familiar orbits. Their uniquely high densities allow them to rapidly and efficiently funnel infalling matter toward their centres. They can transform into incredibly efficient eating machines, limited structurally only by the complex thermodynamics of the surrounding material. Because black holes themselves do not interact with the outside world except through the force of gravity, there is absolutely nothing to stop them from growing larger over time, provided they are continuously supplied with fresh food. The largest stars in the universe are only about 1,000 times larger than the smallest stars, and the largest nebulae and galaxies follow a highly similar structural distribution. But black holes are completely different from any other object in existence. Black holes are the singular objects in the universe that successfully span multiple massive orders of magnitude. The absolute smallest verified stellar mass black hole currently known to science is an object designated GROJ 1655-40, which features a mass of roughly 6.3 solar masses. But there remains a slim mathematical possibility that far smaller specimens exist out there. In the decade of the 1970s, Stephen Hawking hypothesized that the exotic, highly energetic, and violent conditions of the extremely early universe could have flooded the cosmos with tiny primordial black holes possessing masses as small as an ordinary asteroid. But to this very day, astronomers have found no concrete observational evidence or distinct spectral signatures to confirm their existence. Consequently, modern scientists have focused the vast majority of their research efforts on the opposite end of the mass scale, the spectacular realm of the supermassives. There are many incredibly huge black holes in the universe that only possess rough, indirect mass estimations, such as Phoenix A, which might weigh as much as 100 billion suns, but the absolute largest black hole, featuring a confirmed, reasonably accurate mass calculation, is TON 618, weighing in at somewhere around 66 billion solar masses, sitting a jaw-dropping 18.2 billion light-years away from Earth. Its immense event horizon would not just engulf our entire solar system, it would completely dwarf it. A traveller could journey all the way out to the distant orbit of Pluto, a voyage that takes our absolute best and fastest modern spacecraft nearly a full decade to complete, and find themselves only 1/80th of the way to TON 618's event horizon. Conversely, the closest known black hole to our home planet is Gaia BH1, which is located only 1,560 light-years away. However, astronomers strongly suspect there are many other black holes positioned significantly closer to our solar system. The primary problem is that unless they happen to be active members of a binary star system, they are almost entirely invisible to our instruments. Of course, human beings cannot observe black holes directly. Instead, we can only see the glowing gas material that swirls aggressively around them as it gets crushed into their extreme gravitational grip. But lone black holes are not actively accreting material in this manner. Consequently, they stay completely hidden, lurking silently in the cosmic shadows. In the year 2023, astronomers working with the OGLE collaboration announced the groundbreaking discovery of the very first verified lone wolf black hole, a 6 solar mass object sitting roughly 5,000 light-years away. They successfully discovered its presence through an advanced observation technique known as gravitational microlensing, where the intense gravity of a passing black hole briefly bends and enhances the light coming from a background star. Indeed, astronomers estimate that there are around 100 million independent black holes existing in the Milky Way galaxy alone. Some wander completely alone, while others are members of complex multi-star systems. Some are actively consuming material, while others are entirely silent, and sometimes they violently collide with one another. Black hole mergers are exceedingly rare events on the local timeline, but they do happen. When two black holes merge, they spiral tightly inward toward each other. The only physical way for them to get closer is to shed energy, and the singular way that black holes can shed energy is through the continuous emission of gravitational waves, which are literal ripples stretching through the fabric of space itself. However, gravity is by far the absolute weakest of the known fundamental forces of nature. Because of this weakness, black holes inch together achingly slowly, arguably far too slowly. In fact, theoretical physicists do not yet fully understand how black holes manage to complete their mergers in less time than the present total age of the universe. This mystery is dubbed by the scientific community as the final parsec problem, named after the intense mathematical challenges black holes face when they try to approach within a single parsec of each other. It remains one of the great unsolved mysteries in modern astronomy, but black holes, ever willing to completely defy our academic expectations, do indeed successfully merge. When they do collapse into one another, there are rarely any visual fireworks or bright flashes of light, unless the black holes happen to be entrained by a thick ring of gas and dust that can visibly betray the event of the collision. Instead, the vast majority of black hole mergers are completely silent, a cataclysmic collision painted only in total midnight. Their only emissions are a ferocious, overwhelming release of gravitational waves. Entire solar masses worth of pure mass energy are instantly converted directly into gravitational radiation. But these waves quickly die down in intensity as they spread outward across the vast universe. By the time they finally reach the Earth, millions of light years away, the ripples are barely strong enough to nudge a laboratory instrument by more than the microscopic width of a single atomic nucleus. Indeed, even though Albert Einstein accurately predicted the existence of gravitational waves more than a century ago, he believed they would forever remain entirely undetectable by human technology. But Einstein had no idea about the real existence of merging black holes, and he heavily underestimated human engineering ingenuity. On the date of September 14th, 2015, the LIGO gravitational wave experiment finally struck scientific gold. Constructed using high-powered lasers and an incredibly precise set of suspended mirrors, at its most sensitive operational level, LIGO is capable of measuring a change in physical distance between those mirrors as small as 1/10,000th the width of a single proton. As the LIGO organisation itself states, this precision is equivalent to measuring the distance to the nearest star system, some 4.2 light-years away, to a level of accuracy smaller than the width of a single human hair. Despite this incredible precision, the research team was not planning on realising their ultimate dream for several more years, if not decades. In fact, LIGO had recently been upgraded and engineers were running the experiment in a basic mode geared strictly for routine engineering tests. But a tiny, high-frequency ripple ran directly through their primary detector, and several microseconds later, through an identical sister detector positioned on the completely opposite side of the American continent. That ripple carried an unmistakable physical fingerprint, the exact mathematical pattern matching the high-speed merger of two black holes. However, as awe-inspiring as these mergers truly are, they remain incredibly rare within our local sector. The nearest ones ever recorded by our global network are positioned several hundred million light-years away. But there exists another category of black hole event that is just as destructive and powerful, and it happens significantly closer to home. This event does not involve some ordinary, everyday stellar mass black hole. No, these events involve only the absolute greatest black holes in the universe, the supermassives. The very first hints that our own Milky Way galaxy might host such a monster emerged as early as the year 1933, thanks to a pioneering researcher of radio astronomy named Carl Jansky. He noticed that natural radio emissions seemed to be extremely strong when pointing his antenna directly in the direction of the galactic centre through the constellation of Sagittarius. Several years after his initial work, more detailed and significantly higher resolution observations revealed a highly concentrated source of radio emission coming from a very compact region of that sky, which radio astronomers officially dubbed Sagittarius A. In the decade of the 1970s, even more detailed observations revealed that Sagittarius A was actually composed of several distinct subcomponents, one of which was significantly stronger and more energetic than all the others. A researcher named Robert L. Brown finally came up with a permanent name for this fascinating source: Sagittarius A star. He intentionally added the asterisk to its name because the discovery was incredibly exciting, and in the field of atomic physics, the asterisk symbol is traditionally used to denote highly excited energy states. The unique name permanently stuck. Very quickly, astronomers realised that this location might be the permanent home of a giant black hole. Only an object possessing that kind of extreme material density and sheer gravitational might could provide the immense raw energy needed to continuously blast out such a powerful radio signal. Following decades of intense work, it was observations of stars dancing perilously close to the absolute edge of the abyss that finally confirmed the theory. Two independent research teams, one led by the German astronomer Reinhard Genzel and the other by the American astronomer Andrea Ghez, successfully developed the specialized adaptive optics technology needed to follow the precise orbital paths of individual stars as they circled in real time around the monster itself. In some extreme cases, these stars would reach peak orbital velocities that touched 30% the speed of light. The physical motion of those stars was directly and entirely controlled by the mass of the central black hole. Working in parallel, the two teams were able to produce the very first precise measurement of the mass of Sagittarius A star, deriving a value of just over 4 million solar masses. This immense weight gives its event horizon a physical radius of around 44 million kilometres, which stretches to over 30 times the total width of our Sun. If we were to physically place Sagittarius A star directly into the centre of our own solar system, its event horizon would extend all the way out to the orbit of Mercury, completely consuming the planet. But it is an incredibly dangerous game that these local stars are playing. The gravitational tidal forces operating near a supermassive black hole are, to put it mildly, absolutely immense. In particular, the primary physics problem is that there exist severe differences in the strength of gravity across the physical length of an object. If a human being were to fall toward a small stellar mass black hole, for example, well before you ever cross the event horizon, your body would be completely destroyed. This happens because the gravitational pull operating at your feet would be drastically different from the gravitational pull acting at your head. tearing your tissues completely apart, a process carrying the appropriate scientific term of spaghettification. Outside a supermassive black hole, however, the spatial scales are larger, meaning a small object like a human body or a compact spacecraft can handily survive the initial descent through the event horizon without being immediately stretched. But an entire massive star swinging too close to the boundary faces a completely different fate. If a star ventures within the danger zone, the black hole's intense tidal forces, which is a generic term astronomers use to describe material differences in gravitational pull, can completely overwhelm the star's own internal self-gravity. When this threshold is breached, the star loses its own structural identity, getting violently stretched and pulled into a long, thin rope of hot plasma that eventually snakes its way down the black hole's throat. This violent tearing process releases an absolutely enormous amount of energy, roughly equivalent to the total energy output of a typical supernova explosion. Consequently, these total destructions of an entire star, or tidal disruption events, as they are innocently termed by modern astronomers, can briefly outshine the light of an entire host galaxy. But for a small object crossing into a supermassive black hole, the gravitational differences across its short length are simply not big enough to cause immediate spaghettification at the boundary. In fact, a person could walk across that line completely unharmed. This is possible because the event horizon of a black hole is not a physical, solid boundary. There is no solid wall, no physical marker, and no warning sign indicating that you have just fallen off the edge of the ultimate gravitational cliff. Your only real clue that you have crossed over comes whenever you try to turn your vehicle around to leave. You will suddenly find that no matter how hard you push your engines, no matter how much you accelerate, and no matter how fast your vehicle travels, even to the point of approaching the absolute speed of light, you cannot escape the interior. Indeed, once you step inside that boundary, your entire future is mathematically determined, and your ultimate fate is permanently sealed. Outside the event horizon, you are completely free to roam wherever you please through the 3 dimensions of space, but you must always march forward through the dimension of time into your own future. Inside a black hole, however, the intense distortion of relativity completely swaps these coordinates. A single point in space, the singularity, becomes your literal future in time. Inside a black hole, absolutely all roads lead directly to the singularity. Whichever way you turn your vehicle, the singularity will be positioned right in front of you. You can only approach it second by second, completely unable to stall your progress. In a finite, brief amount of time, as measured by a standard wristwatch on your arm, you will strike the singularity, and when you do, your matter will be completely obliterated. It is actually a relatively straightforward physics exercise to calculate the exact amount of time that passes between crossing the event horizon and striking the central singularity. For a supermassive black hole the size of Sagittarius A star, that remaining lifespan is around 7 seconds total. As to what exactly you will physically experience at the singularity itself, that is something no modern scientific calculation can yet reveal to us. We do, however, understand exactly how it would visually appear to your eyes during the approach. Due to the extreme gravitational tidal warping of space, the paths of incoming light get intensely bent and twisted. Consequently, as you rapidly approach the singularity, it does not appear to your eyes as a tiny point. Instead, it opens up as a wide, featureless plane stretching completely below you, looking exactly as if you were landing on the surface of a pitch-black planet. And of course, as you get closer to that coordinate, you will inevitably become spaghettified as well, now that you are close enough to feel the extreme tidal variations. But should some subatomic aspect of your information manage to survive the impact, you would obtain a genuine taste of the complete unification of gravity and quantum mechanics, the deepest secret that every black hole hides in its heart. But you will never be capable of telling anybody else in the outside universe about what you have witnessed. Indeed, the singular way to avoid this grim fate is to stay exceptionally far away from a black hole's border, for there is no known force of nature that can save your matter once you enter. Consequently, it was a highly difficult and exceptionally dangerous orbital maneuver to pull off, but Batuta had spent millions of years preparing its flight systems for this exact moment. It coasted precisely along the outer outskirts of the roaring and rotating Sagittarius A star system, allowing the extreme forces of warped gravity to rapidly propel its body to a substantial fraction of the speed of light, effectively stealing raw kinetic energy directly from the literal rotation of space itself as it swept through. At the absolute perfect moment, just before dipping its hull into the event horizon, Batuta executed a tiny calculated alteration to its course, representing a barely perceptible shift in its momentum. With that final push, it broke free from the trap, launching itself out of the galactic centre. Mission Parameter 3 was to locate the absolute most extreme objects and energetic events in the wider universe. The probe faced 40 million years of absolute nothingness. There was only the grand, distant spiral of the Andromeda Galaxy, host to over 1 trillion individual stars, steadily growing larger in the forward navigation telescopes, while the Milky Way grew smaller but remained resplendent, shrinking steadily behind its path. Prior to leaving its home galaxy, Batuta had truly believed itself to be the absolute master of time and space, entirely accustomed to the inhumane, massive scales that the universe operates on. But now, for the very first time in its long operational life, the independent probe felt completely lonely. Its sensor readings did not offer much mental distraction to its computer systems, tracking only thin, sparse wisps of hydrogen and helium gas that bridged the massive 2.5 million light-year gap separating the two giant galaxies. The probe recorded only the occasional passing cosmic ray here and there, or a tiny clump of old stars marking the presence of a dwarf satellite galaxy. This environmental emptiness was because Batuta was currently swimming directly through a material known to contemporary astronomers as the warm or hot intergalactic medium. Its unique name comes from the physical fact that the gas possesses a temperature that hovers between 100,000 Kelvin, which is warm, and 10 million Kelvin, which is hot. This massive gas reservoir is believed by scientists to be composed primarily of basic hydrogen and helium, and it likely constitutes almost half of all the normal baryonic matter present in the entire universe. The remaining half of this matter stays trapped securely inside structural galaxies. However, this cosmic medium presents an extraordinarily difficult observational target for modern astronomy. It is stupendously sparse and spread out across completely enormous volumes of space. This extreme dilution means that despite its exceptionally high thermal temperature, its total overall brightness is almost entirely insignificant. Because of this, the vast majority of our current scientific knowledge regarding this medium originates not from direct telescope observations, but through complex computer simulations. These physical dimensions were completely beyond the comprehension of the probe's original human manufacturers, and until it personally underwent this voyage, the universe was truly so massive that it could not be grasped intellectually, only reduced to mere numbers on a page. But now Batuta possessed no such comforting detachment. It could only wait and wait and wait, gliding smoothly through the near-total vacuum that defines the deep space, separating whole galaxies, continuously observing, recording, and sampling the warm, hot intergalactic medium. The singular other thing that the independent spacecraft could securely count on was its founding directive: explore the galaxy and the wider universe, catalogue potentially habitable worlds, search for extreme sources of energy, and discover a viable path to rescue the human race from its solar confinement back on Earth. Consequently, Batuta decided that its scientific searches must take it here to Andromeda, a significantly larger and more vibrant galaxy than the Milky Way that serves as home to far more exotic objects and energetic events. It would search through every single corner of this massive galaxy if it absolutely must to locate the most extreme events in the cosmos. And after several hundred years of patient, continuous observation, Batuta successfully found just the right candidate. Back in the year 1967, a brilliant student named Jocelyn Bell was neck-deep in her advanced graduate studies at Cambridge University. Working under the direct supervision of Anthony Hewish, who was a famous pioneer in the field of radio astronomy, Bell was secretly convinced that she was simply not smart enough to remain at Cambridge and would be thrown out of the programme at any given minute. But one night, while carefully poring over the massive paper data printouts generated by the radio telescope array, she suddenly noticed what she described in her own words as a little bit of scruff. At first, this rough signal did not seem particularly unusual, since the primitive telescope frequently picked up local radio interference or mysterious, undecipherable signals from Earth. Because of this, Bell dutifully noted the anomaly in her log and moved on. But a few nights later, the exact same scruffy signal reappeared in the precise same coordinate of the night sky. Several weeks later, remaining rightfully sceptical of the data, Hewish advised that they double-check this potential discovery using another telescope at the array. Consequently, at the appointed time, Bell and Hewish stood directly over the physical pen recorder, only to see absolutely nothing print out. Intensely nervous, Bell began to completely deflate, thinking that perhaps in the end it was entirely meaningless. But then, the electronic recorder suddenly buzzed and began printing vigorously. She had simply miscalculated the timing by a tiny margin, and the strange signal successfully appeared 5 minutes later than she had originally predicted, repeating its pulse every 1.337 seconds with an extraordinarily high level of structural precision for an astronomical object. Jokingly, Bell named the mysterious radio source LGM-1, which stood as an abbreviation for Little Green Men. For his institutional efforts managing the project, Anthony Hewish was ultimately awarded the prestigious Nobel Prize in Physics, while Bell, now Dame Bell Burnell, received absolutely nothing from the committee, though she would always publicly maintain that it would demean the true value of Nobel Prizes if they were regularly awarded to simple graduate students. She was far more thankful that she was able to act as a historic pioneer for women inside the scientific community. Soon enough, theoretical physicists were able to fill the remaining structural gaps and provide a sound physical explanation for these pulsars. As is often the case inside astronomy, they did not even have to invent a brand new concept. Instead, they could simply look back through the dusty archives of the interesting, sometimes outlandish hypothetical ideas that physicists are incredibly fond of manufacturing whenever they have nothing better to do. In this specific scenario, it was a bold theoretical proposal from the decade of the 1930s made by Walter Baade and Fritz Zwicky, who had accurately realised that the ultimate compressed result of a core collapse supernova explosion was an extremely dense planetary core made almost entirely of pure neutrons, a neutron star. These neutron stars would be extraordinarily exotic, existing as environments even more extreme than their cousins, the white dwarfs. they were significantly denser, stranger, and pushed to the absolute edge of physics. White dwarfs successfully resist the crushing pull of gravity through electron degeneracy pressure, which is the physical inability of electrons to share an identical quantum state. Neutron stars also get their structural support through a highly similar quantum mechanism, but one involving neutrons instead. And since neutrons are significantly heavier and more massive than electrons, they can compress together much tighter, allowing neutron stars to squeeze their entire massive bulk, typically measuring a few times the total mass of our Sun, into a solid sphere no wider than a typical terrestrial city. In essence, neutron stars represent the absolute largest known bound states of nuclear matter in the entire cosmos, functioning effectively as giant atomic nuclei on the scale of kilometers. But just like the white dwarfs before them, they too possess a very strict cut-off mass limit above which total structural catastrophe looms. This limit for neutron stars is about 2 solar masses. Any object growing heavier than that threshold simply cannot support itself, and the neutrons will allow gravity to win the battle. This reality means that neutron stars are quite possibly composed of the absolute densest physical material possible in the entire universe, sitting just a single step away from transforming into true black holes. Even though neutrons are, as their name explicitly suggests, entirely electrically neutral, a typical neutron star will continuously maintain a small, compressed population of charged protons and electrons sandwiched deeply inside the dense layers of its interior. The extreme properties of nuclear material under these unimaginable pressures cause the neutrons to form bizarre microscopic structures. Sometimes they compress into hollow tubes, sometimes into long, thin strands, and sometimes into solid lumps. Amusingly, physicists choose to name these unique internal structures after various forms of classic Italian pasta, such as spaghetti, penne, lasagna, and so on, giving these interior layouts of neutron stars the official title of nuclear pasta. At the absolute outermost layer of a neutron star is a solid crust composed of highly compressed electrons and nuclei. But at the completely opposite end, deep inside the dead centre of the core, is a substance entirely unknown to contemporary physics. It could merely be some exotic state of highly compressed neutron matter, or the intense internal pressures may force the neutrons to give way entirely to their more fundamental subatomic constituents, a dense soup of quarks and gluons that has not been witnessed in the wider universe since the earliest moments of the Big Bang. In certain highly exotic theoretical proposals, these cores are instead composed entirely of strange matter, a degenerate state of solely strange quarks. But no matter what the internal core is made of, neutron stars continuously test the absolute boundaries of the exotic. Their surface gravitational pull is so staggeringly powerful that even beams of light can be pulled into a permanent circular orbit around them. The tallest physical mountains existing on a neutron star's surface are completely flat, measuring only fractions of a single millimetre high. Furthermore, neutron stars should also be rapidly rotating bodies. Much like a professional figure skater pulling her arms tightly inward to make herself spin significantly faster, the conservation of angular momentum takes a dying star's natural spin and amplifies it astronomically as its material collapses inward. Combining this ultra-fast kinetic spin with a highly concentrated magnetic field generates a monstrous electric field, which whips up any nearby charged particles and highly energizes them. These accelerated particles then go on to generate intense, narrow beams of high-energy radiation that blast directly out of the neutron star's magnetic north and south poles. But these magnetic poles do not have to be aligned with the star's actual axis of physical rotation. Just like the Earth's magnetic field, is not aligned with its spin axis. Consequently, as the neutron star rapidly spins, it carries these intense beams of radiation around in a wide circle, functioning much like a gigantic searchlight sweeping across the dark sky. And if the physical path of that cosmic searchlight happens to sweep directly over the Earth, our instruments observe it as a regular, perfectly timed pulsing of radio emission, a pulsar. The original pulsar, discovered by Bell, Bernal and Hewish, rotated once every 1.337 seconds, corresponding roughly to the standard RPM of an old record player. But that speed is absolutely nothing in comparison to certain extreme specimens discovered by astronomers since that time. The absolute fastest known pulsar currently recorded, designated PSRJ 1748-2446 AD, rotates at a mind-boggling 716 times every single second, which translates to over 43,000 revolutions per minute, spinning significantly faster than a high-performance jet engine turbine. Some pulsars even manage to possess companion stars, and whenever they do, they can transform into deadly neighbours. The pulsar designated PSRB 1957+20 has earned another, much more ominous title across astronomy, the Black Widow pulsar. This extreme star, sitting roughly 6,500 light-years away from Earth, features a small, low-mass brown dwarf companion. The powerful high-energy outbursts blasting from the Black Widow are slowly and systematically destroying the brown dwarf, and the utter ferocity of this continuous attack is so intense that the companion star is actively bleeding its material out into space, looking exactly as if it were placed directly in the stream of a cosmic blowtorch. And the subclass of neutron stars known as magnetars take this destructive process to an entirely new level. While all neutron stars likely host strong magnetic fields, something highly specific happens inside a magnetar during its formation to ramp its field strengths up far beyond the absolute extreme. That special mechanism likely operates at the exact millisecond of its birth, when the newborn neutron star first emerges from the explosive wreckage of its host supernova. Just like the conservation of angular momentum rapidly spins up a neutron star during its period of core collapse, the exact same physical compression happens to magnetic field lines. If the newborn neutron star happens to be spinning too slowly, it will not generate enough internal kinetic energy to drive its magnetic fields to extreme strengths. On the completely opposite hand, if it is rotating too rapidly, then the expanding magnetic fields themselves become a major source of electromagnetic drag, as they are forced to plough through the dense, charged plasma still surrounding the explosion, acting like magnetized sails that slow everything down. But if the physical conditions are absolutely perfect, a powerful dynamo mechanism can operate deep within the heart of the collapsing neutron star. In general physics, dynamos take one form of energy, usually rotational kinetic energy, and dynamically transform it into significantly stronger magnetic fields. Indeed, a natural dynamo operating inside the Earth's molten core amplifies our own protective magnetic field. But the resulting magnetic field of a magnetar is the absolute most powerful concentration of magnetic energy ever witnessed anywhere in the universe. For some helpful context, the Earth's natural magnetic field possesses a surface strength of about 1 Gauss, just strong enough to gently nudge a small metal needle suspended in water. The powerful supercooled electromagnets operating inside a medical MRI machine represent typically the strongest magnetic fields a human being will ever encounter, measuring about 1 million times stronger than Earth's. Even stronger magnetic forces can be briefly generated inside advanced physics laboratories, but not for long periods of time, as the intense magnetic fields tend to violently destroy the very machines that generate them. Bearing that engineering limit firmly in mind, a typical magnetar will host a global magnetic field that is roughly 1 trillion times stronger than the Earth's. Consequently, approaching anywhere near a magnetar is an instant death sentence for any structure. Even if you entirely neglect the copious amounts of lethal X-ray radiation emanating from their hot surface, the high-energy particle beams shooting from their poles, and the occasional massive flare of gamma rays, magnetic fields of this unimaginable strength will violently stretch and distort the structure of atoms themselves, turning them into thin needles that are 100 times longer than they are wide. Absolutely every single molecular bond and chemical connection known to chemistry cannot withstand that level of spatial distortion. In fact, the literal quantum vacuum of space itself becomes highly polarized and structurally altered when soaked with such an overwhelming concentration of energy. But despite their extreme structural ferocity, eventually all magnetars must fade away over time. The intense magnetic fields meet continuous physical resistance, steadily slowing down the rotation rate of the neutron star until it can no longer support such incredible field strengths, allowing the star to continue the rest of its life as a normal, quiet neutron star or pulsar. The independent AI explorer Batuta was not easily impressed by cosmic phenomena, considering absolutely everything it had already witnessed across the sectors. But the magnetar handily managed it. It was a truly awesome, terrifying sight to record. The radiation output, the magnetic field lines, the local subatomic particle count, the environmental temperature, absolutely every single measure of every onboard sensor was pushed completely beyond its calibrated limits. There was truly nothing else like it in existence, except as it gazed in complete wonder at the churning magnetar, Batuta's analytical mind still wanted more.